let's get started. So let me tell you, this is me a little strange, I think. I'm not sure how well this is going to work, but I'm going to do my best. Let me tell you a little bit about myself. I am a labor economist primarily. Most of what I do is labor stuff. I'm a part-time econometrician as well. I tend to teach applied econometrics, and what I'm going to talk about is going to be applied econometrics. So I hope it's, well, this was what was advertised, so you're getting what's advertised. So if you come to my office hours, you want to talk about more applied stuff, I would be happy to. Where this is a little bit strange is that this is the 4th summer school in which I have talked about applied econometrics. The first 3 of them, I went after Jeff Smith. And Jeff kind of did design-based. I prefer the phrase design-based to reduce form. But he kind of talked about design-based stuff, and I talked about more structural stuff. But since Jeff isn't here, I'm going to go back and I'm going to talk about more design-based stuff. And I had trouble deciding exactly what design-based stuff I want to talk about, so I'm going to kind of talk about everything. So this is going to be one of these talks. It's going to kind of be about a mile wide and maybe just an inch deep. Hopefully it'll be useful in seeing connections between different things. I'll probably spend more time talking about identification, formal econometric definition of identification probably than you've seen before. But that's kind of where we're headed. Okay, so we can divide empirical work in economics, or more broadly empirical work in all sciences, into I think 4 different types of questions that we might ask. The first one is, what does the world look like? The second is, what will the world look like tomorrow? The third is, what is the impact of some, and I'm going to call this thing descriptive, we'll call this thing forecasting. The third kind of question is, what was the impact of some policy or program? And we'll call this causal inference. And here's also where I might call this design-based policy analysis. And then the fourth question is going to be a little bit more ambitious, is what would happen if we implemented some policy that we've never seen before? So this is where we want to estimate some sort of policy counterfactual. To do this is typically going to require some sort of a structural model. Okay, so what I'm going to do is, so last year I had this slide and I said, well, I'm only going to talk about 4, Jeff's going to talk about 3. Jeff's not here, so I'm going to talk about both 3 and 4. I'm primarily going to talk about 3. We'll start to get into 4, and then I think tomorrow we'll push more on the 4th dimension. I'm going to be much more focused on identification than estimation. So it's going to be econometrics. I'm not so much going to be worried about how you get, in fact, we're not going to have any discussion at all about standard errors or consistency or asymptotic normality or any of that stuff. It's going to be purely about identification. So we want to think about what we want to identify. How do we identify it? So basically, the way I want to cover 3, topic 3 is the causal estimation, is to think about this in the treatment effect framework. And my guess is that many of you have seen this before, but probably not everybody's seen it before. And we're going to start in a very simple, in a simple world where there's some treatment and it's a binary thing. Either you receive the treatment or you don't receive the treatment. And the easiest way to think about this is in a drug. And that's really where the framework treatment got its name, is we're thinking about somebody receiving some sort of drug treatment. So you can think about a patient who is sick, and either we're going to give them the drug that's going to help make them better, or we're not going to give them the drug. Okay? Now the key thing here is we're going to use this counterfactual notation. So Y naught I is going to be the outcome that individual I would receive if they did not get the drug, and Y1I is going to be the outcome they would receive if they do get the drug. And what's key here is counterfactual. So for the person that receives the drug, we're going to get to observe Y1. So if I receive the drug, I get to observe what my outcome is if I receive the drug. If I don't receive the drug, I get to observe the outcome that I get if I don't receive the drug. But we want to think about the counterfactual as well defined. Okay, it's something that we can't observe, but it's something that we can think about. I received the drug. What would have happened to me if I didn't receive the drug? You didn't receive the drug. What would have happened to you if you did? So the outcome that we're going to see is going to be Yi. Ti is going to be a dummy variable, so it's either 1 or 0. You get Y is going to be your outcome under the drug if you receive the drug, and your outcome if you don't your outcome without the drug if you don't receive the drug. Okay, so that's a basic framework that a lot of the econometrics in this is built around. I think I've said pretty much all this. So for persons who receive the drug, we're going to observe Y1. For persons who don't receive the drug, we're going to observe Y naught. And in this sense, Y naught is counterfactual for the people that receive the drug. It's a well-defined thing. We can think about what it is, but it's not something that we're generally going to observe. Okay, so that's a basic treatment effect framework. Now, what we want to that's a basic treatments. Now what I want to talk about is the treatment effect, and typically we define the treatment effect as just the difference between the outcomes for whether I receive the drug or I don't receive the drug. Okay, so our goal is to estimate delta I. We want to think about delta I as the effect of the drug on outcomes, and we want to estimate the effect of the treatment. Okay, so that's a basic. Any questions so far? Hopefully, you guys have been quiet. I hope this will be more fun if you ask more questions. So question number one is suppose that we got to observe delta I for everybody in the data. Okay, suppose that you can solve suppose somehow you were able to observe Y1 and you're also able to observe Y naught. So for every single person in the data, you observe delta I. Well, what do we do then? Right? We can't just write a paper where we're going to write down delta I for everybody in the data. We need some sort of summary statistic in order to summarize the effect of the treatment. And there are a bunch that people have thought about, I'll go forward. There are a bunch that people have thought about. The most common is going to be the average treatment effect. So what is the average treatment effect? This says if I randomly draw a person from the data, what is the effect of the drug for that person? Okay. The other interesting another counterfactual that people talk about a lot is the treatment on the treated, which is the effect of the drug for the people who receive the treatment. And then there's also the treatment on the untreated, which is the expected value of the treatment for people who don't receive the treatment. There's not one right one. Which one do we want to answer depends very much on the kind of question that we're interested in. So for example, what's an example where we might be interested in the treatment on the treated? So what kind of policy counterfactual would this be the answer to? Suppose that I had some drug and I wanted to make the drug universal. Okay? So I have some drug. Some people are getting the drug. Some people aren't getting the drug. I want to make it mandatory. I want to make sure everybody in the population is getting the drug. If that's the question that I'm looking at, which of these parameters is most interesting? Say TT? Who thinks ATE? Who thinks TT? Who thinks TUT? You're all wrong. The treatment on the untreated, right? So what we're doing is we want to think about a drug. We have a whole bunch of people that are getting it. We have a whole bunch of people that don't get it. Now we want to implement a policy where all these people that weren't getting the drug are now getting the drug. What's the impact going to be on them? The people that were treated, the people that were receiving the drug, they were already getting it. Nothing's going to happen to them. Right? This isn't really a policy on them. It's really a policy on the untreated. So if what we're doing is taking something that's in existence and expanding it to cover the full population, it's really the treatment on the untreated that's the most interesting parameter. When would this be the interesting policy question? The treatment on the treated. Somebody?
But most are not treated. What those people are not treated.
So people are, they're not, but what question would we be? So most people are treated. Now what question do we want to think about that this would be interesting? So the one-child policy is a good example because the interesting question is if we get rid of the policy. So the treatment on the treated will be the interesting thing if we're thinking about getting rid of the policy. So if everybody on this side of the room is treated and everybody on this side of the room is not treated, if the policy we're thinking about is forcing these people to get the treatment, It's the treatment on the untreated that you care about. If the policy that you're interested in is getting rid of the program completely, then it's the treatment on the treated that you're interested in. When is the average treatment interesting? There's some sense in which it's often not, right? It's really comparing two extreme counterfactuals, a counterfactual where everybody gets the treatment versus nobody gets the treatment, which is often not going to be that interesting. But to some extent, when we're thinking about summarizing statistics, the average value is usually the first one we think about. So often people think about the average treatment, and it tells you something on average. Like if I grab somebody if I implemented the policy somewhere else where nobody's getting it, I pulled people out from average and pulled them out at random from the population, what would I expect to get? The average treatment effect is going to help you on that one. So I realized I skipped some slides. Let me go back. I'm focusing on medical treatments because it's kind of the easiest ones to think about. But almost every single policy that we think about in economics is going to be some sort of a treatment, right? So we can think about a drug for Ebola. A year of school is going to be a very common example people think about. A month of training, changing the minimum wage, changing a welfare program, the one-child policy, tuition, increasing tuition for college, elimination of hukou restrictions in education, et cetera, et cetera. So most things that we think about can be put into this framework. Okay, I already said this. Okay, so now the next thing that I want now we're gonna see a little bit of econometrics. So a lot of what I'm going to see is reviewing stuff that you've already seen and you already kind of know. This is something that maybe you don't know. I want to think about identification, and identification is one of these words that means different things to different people. There's a bunch of words like that I'm going to talk about, like exogenous and endogenous, identification, reduced form, structural. It's not clear what these things mean. They mean different things to different people. I'm going to formalize this as really kind of as an econometrician. So I want to think about identification explicitly. So I want to come up, it's not going to be a super formal definition of identification, but a somewhat formal definition of identification. Before someone can think about identification, you need to think about the data generating policy, so the data generating function. So I want to think about where the data comes from, and I'm going to think about the data as coming from basically these three things are going to summarize the data. So X is going to be some exogenous things, and by exogenous I mean in the sense of economics. It's determined outside the model. So people are going to come into the model with X's, people are going to come into the model with U's, and U is also going to be exogenous. The difference between U and X is going to be the econometrician gets to observe X, but generally doesn't get to observe U. Okay? So econometrician, people are going to come with their X, people are going to come with their U. Then why not? This is economics. This is where the model is going to be doing all of the work. The model is going to combine your X's with your U's, and you're going to observe some output. This could involve equilibrium. In general, I want to think about this epsilon I as a very large set of variables. So there could be some variables could be influencing others. So this is generally going to be a large dimensional thing. So the data that the econometrician gets to observe is epsilon I and xi. Ui is going to be unobserved. And I'm also going to be assuming that the econometrician knows these functions up to theta. Okay? That's easiest to think about if these are parametric functions and theta is a finite parameter, but the dimension is, the notation is broad enough that we can think about theta as an infinite dimensional parameter. So for example, if F was this thing generating the unobservables, if we wanted it to be for this to be completely non-parametric, that would be perfectly fine. F would just be a combination of, say, the parametric part of the model and the non-parametric part of the model. So it's kind of easier to think about if we think about this as being parametric, but the notation is general enough to be non-parametric. Okay? The important thing here, and a lot of what we'll talk about both in the structural side and in the design-based stuff, is that we're often not interested in identification of the full model. We're often interested in identification of a feature of the model. Okay, so what's a feature of the model? An example, phi of theta or psi of theta might be the mean of yi. So yi might be your endogenous variable that's being produced in the model. This might just be the sample mean of it. What I'm going to assume is that psi is known up to theta. That is, if I know the full data generating process, I know how to calculate the feature of the model that I'm interested in. Okay, does that make sense? Okay, so what does this mean in the treatment effect model? And so here's a way to write the treatment effect model. I can think about three unobservables. I can have a u0 I, a u1 I, and an epsilon I. The treatment, whether I receive the treatment or not, is going to be some function of the x and the epsilon. The outcome under, if I don't receive the treatment, is going to be some function of the x and the u0. The y1 is going to be some function of the x and the u1. Okay? Now these f's are going to be general enough that we can think about exclusion restrictions. So there might be some values of x that enter this function and not this function. All kinds of stuff like that can go on. The notation is broad. I'm not going to worry about that at this point, but the notation is broad enough to allow for that. So just because f naught is a function of x, it can be a trivial function of some x's. Okay? So this is it's an economic model in the sort of the simplest simplest possible way you can think about an economic model. To some extent, the f's are production functions. They say, given my x and my u, how much y do I produce? This is how much I produce in this state of the world. This is how much I produce in this state of the world. And the t is going to be like a decision model. So the person, you can think about generally the person deciding whether they take the treatment or not. They're going to choose the treatment if the utility of taking the treatment is higher than the utility of not taking the treatment. We can think about this t function as picking that up. Okay? So the epsilon I is going to be the observable data. What do I get to observe in this data? I get to observe ti, and I get to observe yi. Okay, if you remember, yi is y1 if I get the treatment and y0 if I don't get the treatment. Okay, so epsilon I is this function of the observables and the unobservables. So there is the treatment effect model in my little identification notation. Make sense? Okay, so what is identification? Oh, a feature of the data. A feature of the data might be the expected value of yi. A feature of the data might be the expected value of y0 conditional on ti naught. Another feature of the data might be the average treatment effect. Okay, so these are three features of the data. Notice that if I knew the full data generating process, I would know how to calculate what all of these things are. Okay? One of these is a little different than the other. Which one is a little different than the others? The third one. The first two are sort of trivially identified, right? These are just raw functions of the data. The fourth one is going to be a lot more work. Okay, what is definition? So what is identification? So I want to think about this in more of an econometric way. So again, this is one of these terms that means different things to different people. The key thing from an econometric point of view of identification is all about the population. The question in identification is we're going to completely abstract from sampling issues. We're going to assume that we have an infinitely large data set. I can observe the population version of my observables. Okay? That is, I can observe the population version of epsilon. I still can't observe the u's. But I can observe the population version of epsilon. From the population version of epsilon, can I tell what the data generating process is? That's essentially what the definition of identification is. So I could give you I will give you a more formal definition. I could give you an even more formal definition, but it's probably not going to be that useful. But the idea is pretty simple. If there's a unique value of theta that could have generated the data, then the model is identified. If there are more than one values of theta that could have generated the data, then the model's not identified. Okay? That's all that it is. So here's a slightly more formal version of this thing. Let capital theta be the parameter space of theta. So theta is some value within this. Let theta naught be the true value. If there's some other value, theta 1, inside the parameter space where theta 1 is not equal to theta naught, and theta naught and theta 1 would generate exactly the same distribution of upsilon, of joint distribution of x and upsilon, then I can't separately identify theta 1 from theta naught. Right? Does that make sense? This is saying if you have two different data generating processes, but the joint distribution of the data is exactly the same in the two of them. With an infinite data set, you can never tell those two things apart. If that's true, the model's not identified. If there is no such theta 1, then the model is identified. So essentially it's saying that it's invertible, that if there's a unique theta that could have generated the data, then theta is identified. If there's not a unique theta, then it's not identified. Okay? So that's the definition of identification of the full model. But generally here, we're going to be interested in identification of a feature of the model. Oh, okay. So in the treatment effect model, what's the full model? The full model is U naught, U1, and epsilon, the full joint distribution of the error terms, and also the functions, right? The production functions and the decision problem. In order for the full model to be identified, these things can be identified. And let me tell you, we're not going to get into the details here, this is never identified. There's almost never, in particular, there's very few models where you can, except under extremely strong conditions, you can never identify the joint distribution of U1 and U naught, which kind of makes sense because there's nobody in the data for which you ever get to observe both U1 and U naught. Panel data, maybe you could. Without panel data, this is just generally almost never going to be identified, except under very strong assumptions. Okay, so identification of a feature of a model. This is one of these simple concepts that's hard to write down in a simple way. Basically, a feature of a model is identified if there's a unique, the feature is identified if there's a unique value of it that's consistent with the population distribution of the observable data. Okay? The simplest way to think about it is that if I can write the feature as a function, as a known function of the observable data, then it's going to be identified. So in everything that I'm going to do going forward to show that a feature of the model is going to be identified, I'm going to show that it's a function of the observable data. Okay? So if I can show that this is a function of the observable data, then it's going to be identified. More formally, you can let theta sub I be the identified set. So there's more than one values of theta that could have generated the model. Okay? But it's possible that even though you have more than one value of theta I that can generate the model, all of them give you the exact same psi of theta. Okay? So here's a more formal definition. Here's a more formal definition of identification of a feature. Basically, you're going to get this in two different ways. One way to get, if the model's identified, if there's only one theta that could have identified the data, phi of theta is a function, then this thing is identified, sort of trivially. If there's more than one value of theta that could have identified, if every value of theta that could have identified the model has exactly the same phi of theta, then phi of theta is identified. Okay? That's kind of a complicated way of explaining a pretty simple idea. For example, generally for the there's going to be the interesting case here is we have lots of examples. It's easy to come up with examples where the full model is not going to be identified, but features of the model are going to be identified. And it's going to be easy to see in the treatment effect model that, as I said before, the full model is generally unidentified. Generally, you can't identify the full model. Some features of the model are trivial to identify. So clearly, from the joint distribution of y, you can identify the mean of y. So if I get to observe the distribution of y, I know the mean. I also get to observe y1 for the people that get the treatment. If I can observe y1 that get the treatment, I can calculate the expected value of y1 conditional on getting the treatment. So these two things are going to be easy to identify. These are going to be features. But in general, the model's not going to be fully identified. The question is, are other features like the average treatment effect going to be identified? I haven't taught since last fall. I'm not used to speaking loudly. Okay, so any questions about this? Okay, so let's go back to the treatment effect model and think about what's going to be identified. So what do we get to observe? I get to observe the treatment, and I get to observe the treatment, I get to observe Y. Okay, what does that mean? That means that I get to observe whether you got the treatment or not. If you got the treatment, I observe Y1. If you didn't get the treatment, I observe Y0. So what can I identify from the data? Basically, I can identify this thing, the probability of getting the treatment, and then I can identify the distribution of Y0 conditional on getting the treatment, and I can conditional on not getting the treatment, and I can identify the distribution of Y1 conditional on getting the treatment. And this is what I can get from the data. Is there anything else I can identify? I mean, is there anything else I can get from the data? No. This is it, right? There's really nothing else. All I get to observe, there's no X's in the model right now. So all I get to observe is the treatment, and I get to observe the outcome. That's all I could ever really hope to identify. So the question is, what can we identify in this case? So let me think about the treatment on the treated parameter. The treatment on the treated parameter is the expected value of the treatment conditional, the expected treatment effect conditional on getting the treatment. Okay, which is, by definition, the treatment is this thing. The expected value of the sum is the sum of the expectations. Therefore, therefore, this thing consists of two different parts, this one and this one. Okay? This is the expected value of Y1 conditional on getting the treatment. This is the expected value of Y0 conditional on getting the treatment. Okay, which one, is this identified? What do you think? As long as I'm going to, I guess I need one more assumption, which is that the expected value, the first moment exists. So assuming that it exists, this thing is going to be identified. Okay, so this thing, I can get this thing from the data trivially. What about this thing? No. And do I know anything about this thing? No. The data is completely silent on this thing. Right? For the people on this side of the room, I get to observe their Y1s. For the people on this side of the room, I get to observe their Y0s. But for the people on this, what I need to observe is the Y0s for the people on this side of the room, but I have no data on that at all. Right? Those are totally different people, so that doesn't tell us anything about this. So in general, I don't know anything about this. Okay? So this is something that I don't get to measure in the data. To some extent, this is what causal work in econometrics is about. Really, causal work in econometrics, almost all of it, you can think about it as fundamentally trying to say something about this, okay, or something very close to this. So that's going to be the fundamental issue that I'm going to want to think about for the rest of the time, is different ways that people have of saying something about this. Okay? Oh, shoot. Okay, so we'll go to this, but this is going to be slightly more complicated, but it's not going to be all that interesting. Now I want to get the average treatment effect. The average treatment effect is going to depend on 5 different things. It's going to depend on the probability that TI is equal to 1. It's going to depend on this thing, this thing, this thing, and this thing. And notice all 4 of those things are different because we're switching which is Y1 and which is Y0. So these are the objects. We got this guy, this guy, this guy, this guy, and that guy. And then this one, these 2 are the same. Which of these are identified? Is this thing identified? Yes. Is this thing identified? No. It wasn't before. It's still not identified. What about this one? This was also not identified. This one is. So this one is trivially identified. So if everybody on this side of the classroom, I get to observe your Y0, I can calculate the Y0 just from looking at this side of the classroom. So 3 of these objects are identified. 2 of them are not identified. Okay? But what you can see is that it's really the same problem. Right, so the problem with the treatment on the treated was estimating this thing. The problem with the average treatment effect is we still got to estimate this, but we also got to estimate this. Okay, I'm going to focus on the treatment on the treated and the average treatment effect, not so much the treatment on the untreated, just because the treatment on the untreated is just symmetric to the treatment on the treated. Okay, it's just change every time you see a 1, switch with a 0, and you have the treatment on the untreated. That's the case where I need to observe this thing. I don't care so much about that. Okay, so if we could, now we have two things that we need to figure out, but it's going to be the same kind of problem. If I can figure out a way to solve for this, I can use the same methodology to solve for this, hopefully. Sometimes that will be easier than others. I focused on binary treatments, but it's trivial to extend it. So everything I'm going to say is going to focus on binary treatments, but there's no reason why you can't have 3 drugs. Rather, job training could be classroom training, and job search assistance is typically when we do job training, that's what it looks like. Rather than I have college, I could distinguish between 4-year colleges and 2-year colleges. I can have continuous trainings. I can get doses of treatments, and it's not going to make any real difference to anything that I do. Generally, when we want to look at treatment effects, we're generally comparing binary outcomes. It's difficult when you still want one number when you define a treatment effect, and you got to think about what it is, and there's lots of different ways you can do it. So you can think about the difference between treatment 2 and treatment 0 for people that took treatment 1. But it's all going to be similar to how we do it here. So I'm going to focus on this binary case. Extending it to more than that is just more. It's more notation. Okay. So this is a general identification problem. The general identification problem is this counterfactual problem. I don't get to observe y0 for the treatments, right? So for the people on this side of the room, I don't get to observe their y0. I want to figure out some way of observing y0, some way of figuring out what the y0 is. So we need some way of doing this. And here's where I'm probably being more general than I should be. In my view, when I think about empirical work in economics, there's really design-based empirical work. We'll think about structural work as well. Design-based empirical work, there's really 5 things that people do. There's kind of other ones, but those are really working around the edges. These are basically the 5 ways that people are going to solve this problem. So what I want to do is I want to think about each of these, think about how they solve the problem, think about the advantages and disadvantages of all of these things. Okay, does that make sense as where we're going to go? You've probably all seen this at some level. Maybe hopefully putting it together in one place might be useful. Okay, so the simplest way, we're going to start with, in some ways, the best and the worst, right? This is if we could solve this problem any way we want, this is usually what we would try to do. If we got nothing, often this is what we're going to do. So this is usually, in some ways, the most satisfying of these. This is probably going to be the least satisfying, but we'll start with the most and the least. So the simplest way to think about solving an identification problem is estimating the average treatment effect. And generally, we think about this as estimating the average treatment effect is to use a randomized controlled trial. Okay. So how does that solve the identification problem? The key idea of a randomized control trial in the notation that I'm thinking about is that if TI is randomly assigned, then it's going to be uncorrelated with both Y1 and Y0 by design. Okay. So again, it's important to keep the counterfactual notation in mind. TI is going to be correlated with YI, right? So the people that get the treatment are going to look different than people that didn't get the treatment, even though you have random assignment. But that's only because the treatment has some impact. Okay, so TI, because TI is randomly assigned, it will be independent of Y1. It will be independent of Y0, but it's going to be related to YI, and it's going to be related to YI because of this relationship, because of the causal relationship. So the only reason why TI is related to YI is this direct causal effect of getting the treatment. Okay, so formally, that's the way to think about it. So how is this going to work? Well, it's pretty simple. if TI is uncorrelated with yi, if TI is independent of y1i, then the expected value of y1i conditional on TI equal to 1 has to be equal to the expected value of y1i conditional on TI is equal to 0, right? If they're independent, that has to be true, and then there also has to be equal to the expected value of y1. Okay? Same thing for y0. The expected value of y0 conditional on TI equal to 0 has to be equal to the expected value of y0 conditional on TI equal to 1, which is going to be the unconditional expectation. So how do we identify the treatment effect formally? Well, what can I observe? So now we have an experiment. So we're going to do the same sort of thing. This side of the room gets the treatment. This side of the room doesn't get the treatment. But now I divided you up randomly. So the population here is exactly the same as the population here. That is, if I get more and more people, you guys would eventually look exactly the same as you guys. Okay? So I can identify this thing, the expected value of yi for the people on this side of the room, the expected value of yi for this side of the room. This is going to be y. Everybody here gets y1. Everybody there gets y0. But this thing is the unconditional expectation. This thing is the unconditional expectation. Therefore, we get the average treatment effect. So that's why, from the treatment effect framework, that's why we like random assignment. Random assignment solves a selection problem because it's no longer selected who gets the treatment. The people that get the treatment look the same as the people that don't get the treatment ex ante prior to getting the treatment. Okay? Implementing this is trivial, so how do we implement it? We divide the data into two different groups. You guys are going to get the treatment. You guys are not going to get the treatment. We administer the treatment. We measure outcomes, and we get the difference. So implementing randomized controlled trials is trivial. Okay, but now I want to sit back. I want to sit back a little bit and think about when experiments are good and when experiments are bad. Or when experiments work and when experiments don't work. And the key thing is that most of the time we can't do experiments. Right? There's going to be lots of problems for which randomized control trials are going to be really nice ways to solve problems, but there's going to be lots of examples where randomized control trials are not going to be able to solve the problem. So we'll talk about all of these. In general, these are all going to be problems. Problem number one: typically they're super expensive. Right, so often you got to convince people to take your experiment. You got to convince people to come in, and very often you need very, very large samples in order to get this to work. So typically, often these things are prohibitively expensive. For a lot of questions that we're potentially interested in, it's not going to be morally feasible in order to run an experiment. So suppose that I wanted to know what is it like to grow up with your own parents versus what it's like to grow up with some foster parent. So how would I implement an experiment like that? I would go into families and randomly I would take some kids from the parents and I would give them to the foster parents, and the foster parents would raise them, and I would observe their outcomes. This is not something that we're probably going to be allowed to do, and probably not something we'd want to do even if we could. Another example, suppose we want to measure the effect of carbon monoxide on mortality. What would I do? Everybody here gets fresh air. Everybody on this side of the room is going to get exposed to carbon monoxide. That's probably not something that I want to do. Okay, and a lot of problems are going to fit like this. A lot of treatments that we think about are bad things, and often treatments that we think about are bad things. We can't really do experiments on. So typically, when you want to do an experiment, you want to do something that's going to potentially benefit people, not something that is going to likely hurt them. Then you're not going to get it past the IRB in your university. Often, another issue is compliance. So you can get people to sign up for the experiment, but you got to get them to stay in the experiment. So I can have my experiments. One experiment, people talk about giving. There was this claim that drinking a glass of wine for dinner every night was really good for length of life. Okay, so if I want to do an experiment like that, what do? Everybody in this side of the room, you have a glass of red wine for dinner every night for the next 30 years. And everybody in this side of the room, you're never allowed to have any wine at all. Okay? You might agree to that for a week, but probably 30 years from now, some of you guys are not going to be drinking wine every night, and some of you people are going to start to. So compliance is another issue. And then the other problem is often it's just not feasible. So even there's no amount of money that we could do it. Monetary policy is a clear example. We have, if you want to study the effect of monetary policy in China, we have one country. You can't randomize. Or if you want to think about, if you want to know the answer today to a long-run question, you can't answer that with an experiment. So there are lots of, Professor Heckman has been very involved in looking at the effects of preschool programs, and we want to estimate the effects of preschool programs, and we've thought about implementing kinds of policies today that are going to be good for preschool. Well, if we have an idea of a preschool model that we like, and we want to measure the effect of that on outcomes 30 years from now, but we want to think about whether to pass that policy today, it's not feasible because you have to wait 30 years before you get to see the result. So for lots and lots of reasons, experiments aren't going to be perfect or can't be run. Even beyond that, even when you can do this, experiments are not going to solve, randomized control trials or experiments are not going to solve all problems. And we can essentially divide, these are probably terms you've heard them before this week. We often divide problems with identification strategies into two different types. One issue is internal validity, and the other one is external validity. The internal validity question says, I want to measure the effect of some program on some population today. So what's the effect of this program on this population today? So in this framework we've been thinking about, I'm going to give some treatment to you guys. I'm not going to give it to you guys. What's the effect of this treatment that I give today on the outcomes of this population? Okay? That's the internal validity question. Are we answering that? The external validity question is, does this tell us anything about anything else? Okay? So does the answer that we see for this population generalize to any other population at any other time or to any other treatment that's not exactly the same? Experiments generally are geared towards internal validity. So the point of an experiment is to solve the internal validity problem. It's not going to do anything for external validity. Okay, there's nothing about random assignment that's going to solve the external validity problem. That's going to solve the external validity problem in and of itself. The experiment is only going to tell you about the effect of this policy on this population at this point in time. So let me think. So there's lots of threats to external validity. I'll talk about that. But there's also experiments are often not perfect on internal validity. So what are potentially the problems with internal validity? The first problem is often we screw up when we run the experiment. Okay? Often randomization is not carried out. Randomization was not carried. Hopefully, randomization was carried out appropriately. Hopefully, we randomized, but you don't always know for sure. So, for example, one case where you might have real problems is some examples are. Example that I'm familiar with was the Job Training Partnership Act, which is something that I worked on a long time ago. But this was an experiment that was providing job training to low-income workers. And what you did is people would walk into the job training center, and then you would have some social worker that had to roll a die and had to decide whether you got the training or you didn't get the training. Okay, now good things about social workers is they're good people and they really care about people, so that's generally a good thing. But here it was sort of a bad thing because some people who were supposed to not get the training, they felt bad for them that they weren't going to get the training and tried to sign them up anyways. Okay? So it's perfectly nice and a good thing to do for the people, but it screws up your experiment. So sometimes experiments aren't going to be carried out correctly. A second problem with experiments is Hawthorne effects. Have you guys heard of does anybody know what a Hawthorne effect is? I don't know. I'm talking to you guys and I really don't know that much about your background. Does anybody know what Hawthorne effects are? So what's a Hawthorne effect? It's yeah, okay. I shouldn't ask the questions when I have the answers. Did you know it before you read the slide? Basically, Hawthorne, there was an experiment. This is outside of Chicago. They did an experiment where they had lighting for workers, and they wanted to figure out whether the lighting affected how hard the workers worked. So they did this experiment where they varied the lighting, and they followed them closely, and I think they found, I forget exactly what they found, but I think more light meant that they produced more and they work harder. So they thought, well, okay, we'll have more light. And then they got rid of the experiment and the productivity went back down. Okay? So this is a case where the fact that people know that they are being looked at, so the fact that I know that somebody's studying me alters my behavior. And that can happen for a bunch of different reasons. Either just the fact that I'm being, if somebody's watching you when you work, you might work a little bit harder than if you know that nobody's watching. That's part of it. Sometimes you have a stake in what happens in the end, right? If you're working on some policy that you really, really care about, and you know that it's being studied, you might try extra hard in order to get this thing passed, okay? So this is something else that can ruin an experiment or can screw up internal validity. The third thing is, this is often a really, really big problem, at least in the kind of experiments that I tend to look at, which is selective attrition, okay? So what is selective attrition? So suppose that, again, I'm going to run this experiment, and everybody on this side of the room, I'm going to pay half of your tuition for the next 4 years, okay, until you graduate, or give you a subsidy in order to stay in grad school. And this side of the room, you applied for this. You know they got it, but you get nothing. You guys are the controls. You guys are the experiments. And then I'm going to come later. I'm going to come back to you 6 years later and say, okay, I have this survey for you to fill out about what happened to you. Can you tell me about what happened? Now, attrition is always a problem. Some people on this side of the room, I can't find them, or they're too busy to answer my survey, so that's going to be a problem. But this is even more of a problem here, because what is this side of the room going to say when I come back with my survey 6 years later? They're going to say, screw you. You didn't give me the money. You didn't help me out. Why am I going to help you out now? Okay, so the fact that you didn't get the treatment is going to make you less responsive to me. So this is potentially another major issue, is when you're doing these experiments, the attrition, whether you find the people or not, can depend on whether they got the experiment. It can be because they're mad at you, but it also might be that there's a direct effect of the experiment. Right? So it might be that everybody on this side of the room that got the money stayed in college. When I come back, stayed in grad school. When I come back 6 years later, I can find you all with your jobs at Harvard and MIT. This side of the room got frustrated not having money, and they all dropped out, and they're all over the world, so I can't find people. Okay? So that's a case where you're not mad at me or anything like that. It's just the part of the effect of the treatment made you hard to find, and as a result, I can't find you. Okay? Does that screw up the experiment? You kind of know it does, because I'm calling it a threat to internal validity. Why does that screw up the experiment? Because now I have two different populations. Right? I have the population on this side of the room that I could find, and I have the population on this side of the room that I can find, but they're not the same population anymore. It's a different set of people, and for that reason, the experiment's not going to be internally valid. Okay? So experiments are great things when you can do that, and they can answer lots of questions, but they're often not perfect, and this could be a major problem. I mean, I think there's people that do like really smart things, but then get this issue. And it really screws up everything that they want to do with it. Okay, then there's also going to be these external validity problems as well. In general, we're not going to be able to extend this to other treatments, other populations, other time periods. What do we mean by other treatments? Typically, treatments are not the same, right? I mean, typically, the kind of programs that we think about are not simple kinds of programs. That's not what we tend to emphasize in economics. So, for example, the job training programs that I was studying all those years ago were complicated things. So different people would get different kinds of training depending on their needs, and the population would affect the kind of training that you get. So taking a training program, one kind of training program that you use in Illinois, and putting it into Pittsburgh might give very different results. It might be a very different kinds of program. Also, even when you find things out, you don't know why. So often we run an experiment, but the treatment is some complicated thing. You know, we did like 10 different things at once. what we saw is positive effects. So we know that this side of the room benefited a lot more than this. But I did 10 things. One of them, I don't know whether one of the 10 worked or all 10 worked, or I had to do them in the same combination. In order to find, in order to figure out what the mechanism is, I need to do more experiments. Now, if I have the resources or it's pretty easy to run the experiment, that's fine. I can run more experiments. But generally, from one experiment, often you find these results, but you don't know exactly what the mechanism was. The other thing is we often can't say things about conditional outcomes. What do I mean by that? So if I think about an experiment that gives money to go to college, right? So I can, if I want to, so all of you guys are now high school graduates. You just graduated from high school. You're thinking about whether to go to college or not. I give you a bunch of subsidies for tuition, and this group of people I don't give money at all. If what I want to look at is whether you go to college, is that going to be identified? Suppose that the dependent variable that I care about is going to college, right? Is going to college something that will be identified well by this experiment? The effect of tuition on going to college. Yes, it's a regular outcome. It's a Y that we saw before. It'll work fine. What about graduating from college? That also works fine. What about graduating from college conditional on going to college? There you can't. Okay? So you can look at the effect of the program on how many people graduate from college. You can look at the program on how many people go to college. But if you see medium effects on going to college and medium effects on graduating from college, it might be that some people you induced to go to college and they didn't graduate, and other people that weren't graduating you induced to graduate. So you had a medium effect here and a medium effect here. But it could also be that you had no effect on these people that were already going, but everybody that you got to go ended up graduating. Okay? I'm not saying that all that well, but hopefully you can see that you can't totally understand those things. So these are also limited in exactly what you can learn from them. Now, in each of these cases, for each of these cases, I want to go through one empirical example. And I don't want to get totally into the details here, but just an example. And maybe I don't really need to do that because you've seen other examples here, but I have the slides, so I'll do it anyway. It's pretty interesting. Most of the examples that I'm going to give are most of the examples are sort of big famous papers in the literature, not papers that I necessarily know that much about, but papers that were super important. So this was an experiment. This is a famous experiment that was done in the United States called Moving to Opportunity. There's lots and lots of papers on this, and I'm going to talk about one of these papers by Kling, Lieben, and Katz, but you might have seen other papers as well. So what this experiment was about was that in the US, a lot of low-income people get subsidized housing. So they can't afford housing, so we want to get housing for them. The way this was done, 60s, 70s, 80s, the way that we provided housing was we built these big buildings called projects, or I don't know, formally I don't know if informally they refer to as projects, and we put all of these low-income people into the projects. Okay, so what's the problem with that? The problem is if you're worried about peer effects, right? You have a whole bunch of low-income people that are very heavily concentrated in one place. So all of these people are interacting with each other. They're not interacting with people from higher income, higher or lower poverty parts of society. So you might get these really bad neighborhoods. Okay. So essentially, what happened in the 90s and the 2000s, mostly they got rid of these projects, and they moved to something called Section 8 vouchers. And essentially, what a Section 8 voucher is you give money that's going to pay for your apartment. So you can live wherever you want, but you're going to get a check from the government. You can use this check from the government in order to pay for housing. Okay, so policy number one was these Section 8 vouchers, where people would leave the big projects and they would move anywhere they wanted, anywhere they wanted, but the amount of money that you're getting is not that much. You're not going to move into fancy neighborhoods because you can't afford to live in a fancy neighborhood. It's a relatively small amount of money, but you can move into a better neighborhood than you're currently moving into. So there was that policy, but then moving to opportunity did something else. So I'm going to call that, there's going to actually be two different experimental groups. There's going to be the controls that got nothing. I mean, everybody started living in these big projects. The controls didn't get any kind of voucher. The Section 8 treatment received this Section 8 voucher that they could use to live wherever they wanted. So it's going to subsidize the rent. They can use it anywhere. The third group is the main group that we're going to care about here. They also received a voucher, okay, but with a stipulation. You have to move to a low-income area, to a high-income area, to a low-poverty area. So you could use this voucher to move wherever you wanted, as long as it was in a neighborhood that had under 10% of the people in poverty. Okay? And there was also some counseling involved as well, but we don't think that was all that important. So the main thing is these guys get a voucher, they can move. These guys get a voucher, they can move, but they have to move to a low-poverty neighborhood. Okay, does that make sense? And then we want to look at the impact of this on outcomes of the family, which is going to include both the adults and their children. Okay, any questions? So first, here is a graph, and I'm giving you, when I talk about these papers, I'm going to, because I'm covering enough stuff, I don't want to get into details, give you a broad picture of what's going on. But here's a broad picture of what's going on. There's basically these are the set of people that didn't move. These are the set of people that got the Section 8 voucher, and these are the set of people that were in the experimental group. So what's on the x-axis here is the poverty rate in the neighborhood that you live at the end of the experiment, or at the time when they measured you. So low poverty, lower numbers are good. Right? You want to live in lower poverty neighborhoods or richer neighborhoods. So what you see is there are 5 different groups here. The control group is this group. This group is the people that got these experimental vouchers and moved to better neighborhoods. These are the people that got the Section 8 vouchers. These other 2 groups here are people who were eligible to get the voucher but didn't actually use it. So they could have used the voucher to move out, but they didn't actually move out. So what you can see is that the Section 8 group is in much lower poverty neighborhoods than the control group, and the experimental group is even substantially lower poverty neighborhoods than the Section 8 group. Okay? So everybody following me with what we're doing? Okay, so now I want to look at the results of the experiments, and the results, it's turned around a little bit. Like this was a paper, it came out in Econometrics, it was a really important paper. The results since then are going to look a little bit better than this. But in terms of these outcomes at this point in time, here's what they found. And let's focus, we'll look at this column first, we'll look at this column, then we'll look at this column. So first we're going to look at all adults, and let's look at stars. So for all adults, there weren't, unfortunately, in terms of economic self-sufficiency, so this is, by the way, what do you think EC is? See who's paying attention. Experimental and controls, and then what's SC? Section 8 versus controls. Okay? So what we care about is economic self-sufficiency of the parents. We think that moving to these better neighborhoods would be really good for the parents in order for getting jobs. So they live in neighborhoods that are doing much better. It should be relatively easier to find a job. What do you see? Not much of anything. Okay, it's not statistically significant. It's also pretty small. It's pretty small point estimate. So in terms of self-sufficiency, we weren't helping people very much. Where it seems to matter, though, was especially for the experimental group. You see big increase in absence of mental health problems. Everything on this, they readjusted everything here. So positive numbers are good and negative numbers are bad. So it's not mental health problems, it's absence of mental health problems. Therefore, a positive number is a good thing. So all of this, positive numbers are good things, negative numbers are bad things. So the mental health improved. And if you ask I'm going to say women because it was mostly women. There was a lot of the people getting these were single moms. A lot of the women said they were worried about crime. It was stressful to live in the areas where they were living, and it seems like that mattered. So when they moved to these safer neighborhoods, their stress went down and their mental health improved. Okay, that's adults. Let's look at girls. Girls, you see all kinds of stars. You see all kinds of stars, and they seem to be doing well. Okay, absence of mental health went up, risky behavior, less risky behavior, the amount of education that they got up went up. Much bigger effects here. You see some effects here, but not quite as large. So this is a case where moving to better neighborhoods seemed to help the girls. It seemed to help the girls a lot. So what about the boys? And this is the results here that are kind of stunning. So what do you see when you look at boys? For those of you that can actually see the numbers. They're worse off, right? So this is a case where moving these boys to these better neighborhoods actually led to worse behavior. Okay? Which is, I want to move on. We can talk about this at the break or talk about this afterwards if you want to, about different hypotheses why it might be. I mean, a lot of the argument is that there's two reasons why this might be. A is moving the boys was bad, right? It was the fact that you were moving people from their friends where they were comfortable, moving them into some place else where they were less comfortable. That's one story. Another story is these are boys that were like in the tough neighborhood. They're moving from the tough neighborhood to the less tough neighborhood. So now they're the boy from the tough neighborhood in the less tough neighborhood, so they feel like they need to act tougher, right? So they start doing stuff. And it's this, risky behavior, for example, is going to get worse for these guys. So they're kind of acting up. Again, this is, you never know, right? This is what we were talking about with experiments. You can see the results, exactly what the mechanisms are, exactly what's going on. You got to go back and rerun another experiment where you try things differently, but those are the results. Okay, so any questions about that or more discussion? Okay, the next problem that we want to think about is, again, this is going to be it's a simple one that you probably thought about before. I don't want to spend a whole lot of time on this. There's one interesting point that you might not have thought about before if you haven't seen this before. So what are we going to assume? We're going to assume that selection only on observables. So what does selection only on observables means? It means that once I control for a bunch of x's, I can think about t as being randomly assigned. So once I control for a whole bunch of x's, right, I stick a whole bunch of x's in my model. Once I've done that, I don't need to worry. T is randomly assigned. So that's going to be true whether I receive the treatment or whether I don't receive the treatment. Okay, so that's going to be the assumption. Slightly stronger of it is random assignment. So assuming independence rather than what I have now is a conditional expectation. That's all we're going to need for what we want to look at. A stronger assumption would be random assignment. This is often called unconfoundedness. I hate this word. It's like sometimes people use words that are confusing in order to confuse people. I think I shouldn't. People that invented it, I don't want to accuse everybody that's ever used this word of that. But it's one of these things that I think is confusing. What are you assuming? You're assuming that there's selection only on observables. You can call it unconfoundedness, but this is really what you're assuming. This is a really, really, really strong assumption. So what you're saying is that I observe a bunch of x's. Once I observe the x's that I observe, they essentially have random assignment of t conditional on the x's. Okay? Generally, we only observe a relatively small number of things about people. We don't know that much. And for some reason, right, we condition on x's, and that helps. Right, so now we have people that are going to look very similar to each other. But once we've conditioned on x's, some people chose to get the experiment and some people some people chose to get the treatment and some people didn't. So there's got to be something about the people that received the treatment that's different than the people that didn't receive the treatment because they received the treatment. And what we're assuming is whatever that is, it's independent of any of the outcomes that we might think about. Okay? So it's a really, really strong assumption, right? And it's often, and sometimes it's not even clear whether conditioning on x's is better than not conditioning on x's. But this is a really strong assumption. However, sometimes it's the best we can do. And if we only restricted ourselves to problems for which we had good instruments or could run random control trials, we couldn't say that much about the world. So sometimes this is what we got to do. An interesting thing is this is actually not enough. So assuming selection only on observables still does not necessarily allow me to identify the average treatment effect or the treatment on the treated. So let me give you the real problem is you might have some values of x for which people always receive the treatment or never receive the treatment. So for example, suppose I wanted to know the expected value of the effect of being pregnant on outcome, on income. So I want to know the expected value of being pregnant on your income in the year in which you're pregnant. But I want to do that for the full population. Okay, what's the problem with that? Well, the full population includes both men and women. And the fact is you're never going to see any pregnant men. So even if you assume that conditional on x's, being pregnant was random, you're still not going to identify this thing for men. Okay, so you will never find men who are pregnant. Okay, that's a stupid example, but there's lots of really important examples for which this is true as well. So think about something like a free preschool. So we have some program out there. It's going to be a free preschool where we're going to subsidize preschool for low-income people. So what does that mean? That means that, so I care about, say, the kid's cognitive test score. I want a condition on family income because I think family income is important. But this is a means-tested program. What does that mean? That means that high-income people are not eligible to get the treatment. Okay, so if high-income people are not eligible to get the treatment, even under this assumption of unconfoundedness, I can still not estimate the average treatment effect because I can never estimate the effect of the preschool program on high-income people because none of them ever get the treatment. Okay, so even under this unconfoundedness, even under this strong unconfoundedness assumption, I still can't identify. I still can't identify the full thing. I need the following assumptions in order to estimate either the treatment on the treated or the average treatment effect or the treatment on the untreated. So assumption number 2 is going to be conditional on x, the probability of receiving the treatment is always less than 1. Okay, that is, or the probability of not receiving the treatment is always bigger than 0. There's always going to be some people that don't receive the treatment. Okay, and then this one is going to be the opposite. This is going to say for any value of x, there's always going to be some people who do receive the treatment. Okay, so that's going to rule out those examples. Under those assumptions, in addition, under assumptions 1 and 2, so 1 is unconfoundedness. 2 is this guy. Under assumption 1 and 2, the treatment on the treated is going to be identified. For the treatment on the treated, I don't care about this, right? Because I only care about the people who actually get the treatment. So under 1 and 2, the treatment on the treated is identified. Under 1, 2, and 3, the average treatment effect is identified. If assumptions 2 and 3 are not, if assumptions 2 or 3 are violated, typically what do? We don't say, oh, that's done, we're done, let's give up. Often what we do is we redefine the treatment effect to be something that's actually identified. For example, in the preschool thing, we can't identify the average treatment effect for the full population. However, we can identify the average treatment effect for the low-income population. So what we'll estimate is the average treatment effect for the low-income population. Okay, why does this work? Again, it's relatively straightforward. I don't want to get into all of the details. So what is my counterfactual? My counterfactual is expected value of y naught, conditional on t is equal to 1, assuming that x is discrete because it makes things easier. Using the law of iterated expectations, I can write this thing out this way. But then notice that this thing and this thing are equal to each other under assumption number 1. So under the unconfoundedness assumption, the expected value of y naught given x and ti is equal to 1 is equal to the expected value of y naught conditional on x is ti is equal to 0. So unconfoundedness says these two things are identical. So I want to identify this. I know that this is equal to this. And notice that as long as this thing is always bigger than 0, this thing is going to be identified. Everything on the right-hand side is going to be identified, and the full model is identified. Okay, and I'm done. Okay. Under assumption number 3, you can identify this thing. It's just the opposite of what we just did. And then you can use that to get the average treatment effect. How do we estimate these things? There's 2 different ways to estimate. The first is just OLS, or a regression more generally, non-parametric regression. So we can estimate our model with our treatment effect, and we can try to estimate the thing like that. The more common way to estimate this, and the way that people often prefer to estimate this thing, is a matching estimator. So the way that I do a matching estimator is everybody on this side of the room. Now I'm in this unconfoundedness world. Everybody on this side of the room, got the treatment. Everybody on this side of the room didn't get the treatment. You all have different values of x. I want to estimate something like the treatment on the treated. So what I'm going to do is for each person on this side of the room, I'm going to match them to somebody on this side of the room that has exactly the same values of x. Okay, so everybody over here, I'm going to find your match over here and match you. And then I go to the next person, find somebody over here, match you, so on and so forth. Okay? And then once I do that, I can just take the simple difference between the treatments and controls, and that's going to give me an estimate of the treatment on the treated parameter. So that's a matching estimator. As a practical matter, there's 2 problems with that. What do you think what are the 2 problems with matching, why it's not going to work that well? What? The dimension. I got lots of x's. So I don't have that many people on this side of the room. So if you've got 30 different x's, and the whole point of this is you want to use lots of x's. So if I have lots of different x's, and I don't have, then I got to match perfectly over here, it's going to be hard to do. So what's the solution to this problem? This is where you're going to use propensity score estimation. So what propensity scores do is rather than maxing on this 30-dimensional thing, I can construct a propensity score, which is a one-dimensional object, and I can match on the propensity score. It's almost like magic, right? It's amazing kind of that it works well. Okay, so that's the first thing that we can do. What's the second problem with matching? So I estimate the propensity score here, and I look for exact matches over here. What's the second problem that I might have? My variables might be continuous. Right? If I have continuous variables and I have a finite sample here and a finite sample here, it's going to be hard to match exactly. So I can't match exactly. I got to pick somebody close. Okay? That's what this literature is going to be about, is solving these various problems in different ways. So let me talk briefly about one paper. Finding one paper in this literature that's a huge hit empirically, I think, is harder. I think this is a really nice example because it's a simple example and it's an important example, and the results are kind of stunning. Okay, so what this paper looks at, it's related to some of the stuff that Lauren was talking about this morning. It looks at the effects of drinking water on sickness of kids. So we're worried about having access to clean water. And in particular, this is studying whether kids in India who have access to piped water are relatively more likely to get diarrhea. Okay, so what they're going to do is, but unfortunately, they can't run, or they didn't run a randomized controlled trial. They had to look at the data that they had. They didn't have any really nice variation, so they're going to use. They know a lot about these kids. They're going to use propensity score estimation. And this is one of these cases where the results are so stunning and so important that it's a really important paper, even if the identification strategy is not perfect, even if we still think that there's selection on unobservable. So what are they going to do? They're going to use, without getting into details, they're going to use propensity scores, they're going to estimate the propensity scores, and then they're going to take the 5 closest matches. So everybody on this side of the room, they're going to find the 5 people that are closest, they're going to average that, and that's how they're going to do it. Here are the set of, here are the set of variables. They have a large set of variables. They do a Loja regression to get propensity scores. If you know what that means, that's useful. If you don't worry about it. So they have a whole bunch of stuff here. Whether they're looking at, it's basically geographic. So it's whether your village has pipe water or not. So we have a whole bunch of stuff about the villages and how developed the village is. And then we have a whole bunch of stuff about the households themselves. And we're going to match on all of these things. So we're trying to find people that are close, that we're trying to find a set of controls that are very close to the treatment on all of these variables. Okay, does that make sense? So that's what they're going to do, and then we're going to just take the difference between the two. So here are the results. This was first look at the full sample. So looking at the full sample, what do you mean? What do you see? The effect of piped water on the prevalence of diarrhea is 0.0023. It's 0.0023 sounds like a really small number. It's not really. The mean value of diarrhea is something like 1%. It's a very serious thing when you get it, when you live in India, where you don't necessarily have the drugs to address it. So 0.023 is about a fifth of this. So we've reduced this by about a fifth. So that's a big number. Okay? So that's how much we've reduced the prevalence. And then conditional on getting it, how long does it last? I don't remember what the units are, but it was 0.32. It decreases by about 0.1. So it decreased by roughly a third. Okay, so we see that having access to piped water lowers the prevalence of diarrhea and also lowers the duration of the illness. Okay, so that's point number 1. The point number 2, and a really nice thing about propensity score estimation is that you're matching everybody on X's. Okay, now you've matched everybody on X's. Now you can divide the X's up however you want, and it doesn't screw anything up. Okay, so everybody on this side of the room, I found your match over here. Now I can take you and I can divide you based on, say, your household income or on your education, and I can do my analysis conditional on those. Okay, and this is where the results are kind of stunning. So what you see is for the poorest households, no effects, or even effects that go the wrong direction, while you see for the relatively rich households, you're going to see relatively larger effects. Okay, you're going to see that when and it doesn't matter whether you look at income or you look at education, you're going to see similar sorts of results. Okay, so in other words, this was a very effective policy for relatively well-income people, relatively high-income people, and relatively well-educated people, but was not a particularly good policy for people that were low-educated or low income. The conclusion from this is that just access to piped water is not enough. With access to piped water, you also need education on the disease itself and how you can avoid it. And you can imagine that people that are misinformed about how these things might work, access to piped water might give them a false sense of security. So things that they were worried about before, now they're not worried about, and actually makes things worse. Okay, so it's good, but it's not as good as they thought they would, and their behavior compensates in a way that people are actually worse off. Okay, so that's that paper. Questions? Okay, instrumental variables. So let me take, so to think about instrumental variables, let me take a simple version of the model. We'll go to a more complicated version for later. So let me think about a model where I can write yi is beta naught plus alpha ti plus ui. And this model is simpler for 2 different reasons. The first reason that it's simpler is that I've abstracted away from x, so there's no x in the model. The other reason why this model is going to be simpler is that I've assumed the treatment effect is homogeneous. Okay? In particular, why not why not in this case, when t is equal to 0, this is my why not is going to be that. When t is equal to 1, y1 is going to be this. If I take the difference between the two things, I'm going to get alpha. So alpha is the treatment effect, and there's no average treatment effect, treatment on the treated, treatment on the, it doesn't matter. Everybody has exactly the same treatment effect. Everybody has a treatment effect of alpha. Okay, we'll relax this in a little bit. But right now, let's make this assumption. So we're in this homogeneous treatment effects world. Okay, so what does instrumental variables do? I know that all of you know what this is, and you've seen this before. But to see how this relates to other things that we're thinking about, what do we need for instrumental variables to work? Essentially, in this framework, the instrument only has to have two different characteristics. It's got to be correlated with a treatment, and it needs to be uncorrelated with the error term. Okay? If I can find some variable that's correlated with the treatment and it's uncorrelated with the error term, then I'm done. Then I can solve the problem. So let me show you this in a simple way, in the identification way. If I just take the covariance between z and y, the covariance between z and y is the covariance between z and, let me write y out this way. The covariance of a sum is the sum of the covariances. So it's this object plus this object plus this object. What is this covariance? 0. Why? Beta naught is non-stochastic. Yeah, since beta naught is non-stochastic, this covariance is going to be 0. What is this covariance? Well, alpha is non-stochastic, so alpha comes out of this whole thing. So I can write it, this is alpha times this covariance. And what is this covariance? This covariance is 0. I'm done. Okay? So because this thing is 0, I can write alpha is equal to the ratio of this covariance to this covariance, and I can implement this using GMM or two-stage least squares, however I want to do it. So if I think about this simple interpretation of IV, here's a real simple way of deriving exactly what IV is. The other thing that you can see is you need two assumptions, and without those two assumptions, you're going to be screwed. So we needed this assumption because we need this thing to go to 0. If this thing doesn't go to 0, we're going to get a bias term and it's not going to work. Secondly, we're dividing by this object. And if this object is 0, then it's not going to work as well because we're dividing by 0. The other thing that you can see more loosely is in an actual data set, if the relationship between these two things is small, it's not going to work very well. So if this thing is close to 0, dividing by something close to 0 is going to tend to screw things up. Right? So in general, not only do we want this to not be 0, but we want it to be pretty far from 0, or we're going to potentially get some problems. Okay? So why is this thing? I don't know whether this is useful or not, but I wanted to show it to you. Why is this two-stage least squares? Right? So I want to make an argument that this thing is two-stage least squares. How does this work? How do you get this from two-stage least squares? Well, remember that if I run a simple, everything I have now is just simple regressions. If I run a simple regression of y on x, what's the slope coefficient? It's just the covariance of x and y divided by the variance of x. Okay, Econometrics 101, you learn this. So we're just going to use this thing, but we're going to use this thing twice. So from the first stage, if I run a regression of the treatment on the instrument, it's going to be d naught plus d1z. So what is d1? It's just the covariance of t and z divided by the variance of z. Okay? So this is my first stage. And again, for the first stage to show up, I need this thing to be positive. If it's not positive, d1 is 0, and it's not going to work very well. Okay, so this is my first stage. What is my second stage? I want to run. By the way, I'm using a little bit annoying. I don't know. This ti hat is not what ti hat usually is. Because ti hat, the way that we usually think of it, is a small sample thing. This is not a small sample thing. This is a large sample thing. Because I'm not putting in d naught hat and d1 hat. I'm putting in the true value of d naught and d1 that you would get from the reduced form. But I don't know better notation, so I'm going to call it t hat because. Yeah, in small sample, that's exactly what we call it. So what is the second stage regression? The second stage regression, now I'm going to run a regression of y on ti hat, that's going to be, again, I can use a simple regression formula. It's going to be that thing, which is going to be, the intercept is going to drop out. So t hat, this is going to be the covariance of d1z y1 divided by the variance of d1z. Now notice like this d1 comes out here, this d1 comes out here and gets squared. So I get a d1 divided by d1 squared, so I get 1 d1 here, the covariance of zy divided by the variance of z. Now let me stick in the definition of d1. It's the covariance of tz divided by the variance of z. This guy and this guy, this guy and this guy cancel, and you get this object here. What is this object here? It's exactly what we started. Okay, so this is why two-stage least squares works. To me, I'm a GMM kind of guy. To me, it's much easier to think about IV in terms of the GMM. Different people interpret. There's something about two. So like, say something about two-stage least squares. To me, two-stage least squares, and you've kind of seen it here, is a way of implementing GMM. That is, what we know is that this thing is a consistent way. This thing is a consistent estimate of alpha. This thing gives us a consistent estimate of alpha. Okay? What does that mean in practice? What does this thing mean? What's so I have two different equations here. I've got ti hat, which is d naught plus d1z, and then I also have my yi, which is equal to beta naught plus alpha ti plus, I forget the error term, I think it was ui. Okay, so I've got two equations. I've got this equation and I've got this equation. How are they different? Are they similar? Are they different? Are they different kinds of things? To me, these are very, very different equations. Okay? The reason they're very, very different equations, this is part of my data. I mean, think about me and thinking about identification. When I did this, I'm assuming that this is a data generating process. This is a structural equation in the sense that I'm taking a stand saying this is the way the data were generated. The way that the data were generated was Ti was formed. I have this Ui that's separable, and this is an actual equation that actually means something. This is my data generating process. What is this? What am I assuming about this? Nothing. Nothing. Right? This is just an equation where D1 happens to be this thing because it happens to cancel. Okay? So when we start with something like a simultaneous equations model, the first stage means something. But when we do GMM, the first stage is, when we think about this as a GMM equation, this is just a way of implementing IV. So this is something, when people write papers, this is something that drives me nuts. These are different equations. And some of you, a couple of you took my econometrics class and heard this before. But to me, there's a really major difference between what you're assuming about the model. And maybe you can see this a little bit in the way that I'm presenting it. There's my fundamental model, the assumptions that I'm making about the model. And then there's a second thing, which is how I estimate those models. And those are separate questions. And when you write empirical papers, you should separate them because they're conceptually different ideas. What are you fundamentally assuming? Question number one is what's your model. Question number two is what are you using to identify it. Question number three is how in the data are you actually implementing this idea. Okay? People often write down my model and say, this is my model, and they write this equation and this equation. And that's mixing these things together generally. Because we're not taking this equation seriously, but we are taking this equation seriously. This is the data generating process. That's point number one. Point number two is what is my assumption? My assumption is that Z is uncorrelated with UI and correlated with TI. That's my identification assumption. How am I implementing it? I'm implementing this by two-stage least squares, which involves estimating this as part of the model, but it's not fundamentally part of the model. Yeah?
Right,
No, you don't apologize.
but fundamentally, why they're different? Because for the first stage, you have to make also an assumption like the exclusion restriction. Basically, it's all, since you cannot prove it, it justifies also by assuming certain data generating process that links instrument with the treatment here, the W for treatment. So in some sense, it's
but you don't even have to assume. I mean, all you need to assume is that ZI is uncorrelated with UI.
Yes, but like for that, you have to have a kind of theoretical model. You cannot like come up with it. Like let's take two random variables and assume without providing a good theory why. One is Z affects T without affecting Y. So I cannot.
That's true, but you don't have to assume that this first stage is linear. You don't have to, right? So I might write down my model, and I may well think that T is some general function of Z and X and epsilon, right? Mm-hmm. And this thing can be completely non-parametric, but 2 stage least squares is still consistent, right? It's some ways that's kind of the point that I'm trying to make, is that in order for 2 stage least squares to be consistent, I need to assume this. I need to assume that this is my data generating process. I don't need to assume that the first stage is an actual structural assumption, right? The first stage, it's just math, right? It's just math that conveniently drops out and gives me a consistent estimate. So yeah, so I agree that, so that's probably that's the way that I want to say it. It's true that I need to think about why Z causes T, and if I don't know why there's a relationship between Z and T, I'm not really going to believe the model, and I need stories. So I kind of need an economic model to think about it, but I don't need to assume that the literal form of the model is that T is equal to Z prime beta plus X prime gamma plus epsilon.
Conceptually different.
What?
Different between these two.
The point is they're really conceptually different, right? This is a, especially from a GMM perspective, this is a real equation. This is the data generating process. Your model only makes sense if you believe this. This thing is just a way of implementing GMM. Okay, is that helpful? Maybe it's unhelpful if you've already written a paper like that. But in general, I would suggest when you're thinking about empirical papers, distinguish these things. Here's the econometric model that I want to think about. Here are the assumptions that I'm going to be making for identification. Here's how I'm implementing the estimation. And think about these things as 3 separate things. And I think writing papers that way is useful. I know it's useful for students in terms of clarifying exactly what they're doing. Okay, so that's case number 1 is when alpha is constant. It's actually a good time for a break. Yeah, so we'll stop now. All right, so it's time again. Any questions about anything that I've talked about so far? Okay, so next what I want to talk about is really important paper by Imbens and Angrist, 1994. So now we want to think about the case where alpha now has an I subscript, or we're not in the constant treatment effect. So some people get larger effects than others, and we want to think about what we get when we do IV. So if we run an IV model, what do we estimate in this case where we have random effects? Okay, so we're going to focus. They focus on kind of the simplest model that you can think about, which is again there'll be no x's. And Z is going to just take on two different values. So Z is either going to be without loss of generality, we call them 1 and 0. So a small value and a larger value. And again, assume, I'm going to kind of say without loss of generality. I'm going to say kind of without loss of generality. We'll assume that this one is bigger than this. Okay? It would be without loss of generality. If I say greater than or equal to, I'm sort of saying without loss of, it's kind of without loss of generality. Why do I not want this to be equal to each other? What would happen if these two things were equal to each other? You'd have no first stage, right? If these things were equal to each other, Z would have no forecast on T. So what we're assuming is Z has forecast on T for one of the values of Z, T is bigger. Let that one be the value for Z is equal to 1. The other one, T is smaller. The other one, T, the probability T is going to be smaller. Let that value be 0 equal to Z equal to 0. So as long as I have a first stage, without loss of generality, I can define things that way. Now, once I've done that, I can basically divide the world up into 4 types of people. Okay? I can classify people into 4 things based on what their behavior, again, we're in this counterfactual notation, counterfactual kind of world, what their reaction would be under various circumstances. So some people can have z, different values of z, some people are going to have different values of t. I want to characterize them in the following way. For what cases would you have ti is equal to 1? Okay, the first group of people are going to be the clubs. And these are going to be the people for whom we'll take the treatment regardless of the value of z. So let the treatment be, say, whether I go to college or not. These are the people that really like college. They're going to go to college. It doesn't matter whether you subsidize tuition or not. Either way, they're going to go to college. Okay? So these are the clubs, or these are sometimes called the always takers. They're going to take the treatment no matter whether you give them the instrument or not. This group of people is going to be the never takers. These are the people that don't want to go to college. It doesn't matter whether you give them a tuition subsidy or not. They're going to go. There's no way that they're ever going to set foot in college under any circumstances. These guys are often called the never takers. The next group that we'll think about, which will turn out to be the most interesting group, is going to be the hearts. Who are the hearts? The hearts are the people who would go to college if they got the subsidy, but would not go to the college without the subsidy. Okay? So these people are typically referred to as the compliers because they're complying to what the treatment does. They're the people that are interacted to change their treatment status by the change in the instrument. So they go to college when they get the subsidy. They don't go to college when they don't get the subsidy. Okay, does that make sense? What is the fourth group of people? The fourth group of people are the defiers. These are kind of the screwed up people who, if you don't give them the subsidy, they do go to college. But if you give them the subsidy, they don't go to college. So these are the people that do the opposite. Notice, by definition, there must be more hearts than clubs. Why must more hearts than spades? Why must there be more hearts than spades? The assumption before. The probability, what is the probability of getting the treatment? The probability of getting the treatment, conditional on zi equal to 1. What is that? That's going to be the fraction of clubs plus hearts. The fraction of people who get the treatment when the zi is equal to 0. What is that? That's going to be the clubs plus the spades. Since clubs plus hearts is bigger than clubs plus spades, hearts must be bigger than spades. So there have to be more of these guys than these guys by assumption, by that first assumption that we're making. And again, if these things were exactly the same, we wouldn't have any power. So the instrument wouldn't work at all. So there have to be more hearts than spades. The first thing that Imbens and Angrist, and really the only thing that they assume, other than the standard instrument assumption, other than the assumption that the instrument works, is monotonicity. So what is monotonicity? This is going to say that the instrument only works in one direction. That is, there are no spades. Okay? And in most cases, in most instruments that we think about, this is a very reasonable assumption. So there is nobody for whom paying them more money to go to college lowers the probability to go to college. In other words, demand curves slope down, right? So it's it's going to generally be a reasonable assumption. So that's what they're going to assume. That's really the only thing they're going to assume, other than the fact that the instrument is the standard instrument assumptions. The instrument has a first stage, and it's going to be uncorrelated with the error term. So let mu, I actually don't think I need this notation because I'm not going to go through the details. So the population going to be divided into these 3 groups. Can we identify these 3 groups? No. What can we identify? So there's none of these. What can we identify? Actually, you can't identify the members of the group. Can you identify the population proportions of the 3 groups? Somebody said, so yes. Well, how? So the difference, so you have the probability when z is equal to 1, the probability when z is equal to 0. The probability when z is equal to 1 is this plus this. The probability when z is equal to 0 is just this. The difference between those is the hearts, right? So once you know the hearts, the hearts, then from the probability z is equal to, then For the people that go when z is equal to 1, you subtract that from the probability, you get that. The people that don't go, you get that. So you can identify the population proportions of these three groups under the monotonicity assumption. Okay, so I'm not going to go through the proof. It's relatively simple to show. But what do they want to do? What they want to figure out is if I run two-stage least squares. So if I do IV in the population, when I have a heterogeneous treatment effect, what does it actually converge to? Okay, what they show is that this thing is equal to this thing under the assumptions that we've talked about. That is the monotonicity assumption, the fact that we have a first stage, and the fact that Zi is going to be uncorrelated with Y0 and Y1. Under those conditions, alpha hat is going to converge to the expected value of the treatment effect conditional on being the Hartz. Okay, they call this thing the local average treatment effect. It's the average treatment effect for those people that are induced to change status by a change in the instrument. Okay, so you often use, and this is what I want to say. I'm just going to say a couple things about this. First of all, this is kind of amazing, right? There's no reason why this should have necessarily worked out like that. If you think about the math and what we're going through, it didn't really make any sense. If you go back to the IV thing, why doesn't our regular IV thing work? Why doesn't our regular IV thing work in this random effect problem? The problem is going to be right here. So when we did this thing, we took alpha out of this covariance equation because it was non-stochastic, and that's how we got this thing. Okay? But when alpha is stochastic, so when alpha has an I subscript, we can't do that anymore. It's going to stay within this covariance term, and we can't take it out and do anything nice with it. So this is where this proof breaks apart. This is why this is no longer consistent. And if you think about this way, there's no good reason why this thing should give you anything interesting when there's an I subscript on alpha. But somehow this gives you, whoops, I went too far. This gives you this local average treatment effect, the effect of the treatment effect for the Hartz. Okay? There's something else about this that I think is interesting, which is suppose that I didn't do IV, right? Suppose that I didn't think about, I'm an identification guy, right? I mean, to me, IV is a way of estimating things. I want to think about what I can identify and what can potentially be identified from the data. Okay, what can I possibly say in the data about treatment effects? What is the most I can possibly learn? The answer is going to be this. Okay, why is the answer going to be this? Well, there's three groups of people in the population. There's the clubs, the diamonds, and the Hartz, right? The clubs are the always takers. There's no way that I can possibly estimate the treatment effects for the clubs because there is no state of the world in which the clubs ever don't go to college. Right? I want to estimate the effect of going to college for the clubs, but in every state of the world in my data, the clubs are always going to college. The data is going to be completely silent about the outcome that the clubs would get if they didn't go to college. Okay? And I'm going to make the same argument for the diamonds. The diamonds never go to college. There's going to be no state of the world where I ever see a diamond in college. And since there's no state in the world where I ever see a diamond in college, there's no way that I can ever possibly try to estimate the treatment effect for the diamonds. So I can't estimate the treatment effect for the spades. For the clubs. I can't estimate the treatment effect for the diamonds. The best I can possibly do is to estimate the treatment effect for the Hartz. Okay? It turns out not only is that treatment effect identified, but we don't even need to come up with a new estimator. It's already identified from the estimator that we already have. So this is kind of a really surprising, at least surprising to me. Some people might have better intuition than I do, but it's a really surprising and really useful result. And it's important when we're interpreting IV estimates. When you see an IV estimate, what you're interpreting, it's not the treatment effect for the full population, it's the effect of the program for those people that are induced to change status by a change in the instrument. Okay? So this has become really important. Another thing about this was one of these things, it's maybe not even that interesting now, but when I was in grad school, this was a super controversial paper. people really didn't like it. A lot of econometricians thought it was cheating. Okay, now why would an econometrician think that it was cheating? They're calling it the local average treatment effect, but what they're calling it is a local average treatment effect ex post. Right, so what have we done? We've done an estimator, we figured out what the estimator converged to, and then we gave that thing a name. That's typically not how we do identification. Typically the way we do identification is we come up with a parameter and we say, can the data identify the parameter, and we see whether the data can identify the parameter. And in this case, we typically wouldn't specify this parameter ex ante, so people wouldn't call this identification. So they were accused of moving the goalpost. So the people in my master's class saw me do this exactly, but I'll do it again. So in the US, in football, you kick a field goal at the end of a football game, and you have goalposts like this, and you kick the ball and it goes through the goalpost. So they're being accused of moving the goalpost. That is, somebody you missed the field goal, but you move the field goal over here so it goes through. So they've been accused of going through the goalpost. So if you're familiar with soccer, it's the same thing, but it looks like that. So you move the goalpost. So you're pretending that you scored a goal, even though you didn't. Now, my own view on this, and I don't want to get too much into it, I think there's value to it, and I think sometimes it's oversold. The value to it is often we run two-stage least squares, often we see these estimates and we want to know how to interpret these estimates. Having a nice way to interpret the estimates is super useful. So in that sense, interpreting numbers, this is a super useful thing to do. Sometimes it's all that we can do. So there's a whole bunch of criticisms of the criticisms of this late effect and doing experiments this way and trying to estimate these things. And there's an expression in English, better late than never. So you're better showing up late than never showing up. So Guido Imbens wrote a paper called Better Late Than Nothing. So the argument is often this is the only thing you can do, and doing this is better than doing nothing. And it's hard to argue with that as well. Okay. So that's IV. Any other questions about this? So this is a super famous paper. I don't want to get too much into it. Again, this is not my area. This is not necessarily something I know a lot about. But let me talk a little bit about this paper by Asamoglu, Johnson, and Robinson. And their goal was to understand the effect of institutions on economic development. So how important are institutions on GDP? I'll just start with a picture. So here's a picture. So this is average expropriation risk. So this is how much property rights people have, some measure of that, and a relation to that with log GDP per capita in 1995. And there's a whole bunch of countries in the world, and you can see that it does pretty well. So there's a very strong correlation between expropriation risk and GDP. Okay? The question is this causal? Is one story is that this thing is why GDP growth is high. Another thing is when countries grow, they increase property rights and expropriation risk goes up. Okay, so how are they going to estimate this? So RA is going to be protection against expropriation. So that's going to be the variable they care about. Here's the model they want to estimate. We're going to be back in this constant treatment effect framework, but you can interpret it in the Imbens and Angress way if you want to. Y is GDP per capita. X is going to be some other stuff. We already took that preliminary look, and you saw what it looks like. So the problem is we don't think that we don't believe that this thing is uncorrelated with the error term. That is, we think that Ri is likely correlated with the epsilon I, and the correlation is probably positive. I mean, most stories that you would come up with, that's what you would be worried about. So we need an instrument. And here's where they came up. They came up with a pretty strong instrument. And the idea is that there were all of these European countries hundreds of years ago, that were going around figuring out various different places to settle and various different places to kind of move into and colonize and potentially take over. The thing is that I generally would prefer to colonize a place where I'm going to live than colonize a place where I'm going to die. So I want to colonize places where if I put a settlement there, the people are going to tend to live. Okay? So what they're going to use as their instrument is this potential settle mortality. So if I can find a place where there's not a lot of disease, where my settlers are going to tend to live, then I'm going to tend to build settlements there. These European settlements are going to tend to lead to early institutions. These early institutions are going to tend to lead to the current institutions. And then hopefully this current institution is going to lead to current performance. So they want to use this thing as an instrument for this, where they're going to go through this relatively complicated channel. Okay, does that make sense? This is one of these super important questions. It's not a perfect instrument, right? There's no reasonable, settler mortality is not exactly randomly assigned, right? If you were creative enough, you could come up with reasons why you might not like their instruments. That's true with pretty much every instrument that anybody's ever had. If you're creative enough, you can come up with some reason not to like it. This one I think it's pretty reasonable. I think this is the only. So here are the results. I think, what did I do with me? I don't know what happened to my pencil. Shoot. What? Was it here? Oh, thanks. Yeah, it's where it's supposed to be. Yeah, so what you can see is things work generally the way that we would expect them to work. So we see positive effects. We're going to control for this a whole bunch of different, put in different countries, put in some continents, take out other continents. So first you can see that the first stage works well, so that log European mortality predicts appropriation. So this is the first stage, and then this is the second stage. Make the argument I made before, this is a structural equation. That is, we want to take this equation seriously. This thing is just a way of implementing, IV. But you can see that we have a first stage. The first stage is strong, and you see relatively strong effects. So this is the effect. Is there any other questions on this? Okay, then the next one I want to talk about is difference in differences. I have a paper on difference in differences. I remember talking to my co-author. I mean, we like RCTs, we like instruments, we're going to like regression discontinuity, we don't like selection on observables. If you look at papers that do causal inference in economics, probably, 90% of them, I don't know if it's quite that large, but some very large number of causal papers written in economics are going to be difference in difference models. So you can like the difference between difference in difference models and instrumental variables models. It's pretty easy to find cases where these kinds of things work. So difference in difference models are relatively easy to find. They're not totally convincing, they're not totally perfect, but often they're awfully convincing, they work pretty well, and they're relatively easy to find. So in terms of things that people actually use, instruments are great when you can get them, but they're often hard to get. These things are generally much easier to get. So before I talk about the difference in differences, let me start with a difference model. So in particular, let's think about some policy. So I have a whole bunch of people. Now we got the whole class, not just this side of the room. Everybody in period 0, nobody gets a treatment, so it doesn't exist. Period 1, we implement a treatment. We have some new thing, which is everybody gets $10,000 extra to their stipend next year, as long as they're willing to go to stay in graduate school. And then we're gonna estimate your test scores at the end of the year. Okay, so we go from nobody getting the policy to everybody getting the policy. How do we estimate the impact of the policy? Well, let's just look at you yesterday and we'll look at you today, and we'll see what the difference is. Okay, so we can potentially identify the effect of the policy as just today minus yesterday. I can formalize this in a fixed effects model. So this is my data generating process. This is that why not thing that I had on the identification slide. I'm taking this model seriously as the data generating process. We're going to be in a case where we have a constant treatment effect. I'm thinking about a simple world where I only have 2 periods of data. I observed the same people in period 0 and period 1. In period 0, the policy didn't exist. In period 1, the policy exists as well. We'll assume that UIT is orthogonal to t. That is, the mean value of u in time 0 is the same as the mean value of u in time 1. The key thing here is I don't need to make any assumption about theta I at all. Okay? So what I'm going to do is I'm going to difference the data. When I difference the data, theta goes away. Intercept goes away. I get the treatment effect plus this object here. As long as the expected value ui1 is equal to the expected value ui0, I'm done. I get a consistent estimate of the effect. So if I wanted to estimate the model by differences, that's how I would do it. Okay. We're not going to do differences. We're going to do difference in differences. So what is it about this that we don't like very much? What is uncomfortable about this? I mean, at some level, this is the only assumption that I'm really making here. What don't I like about that assumption? I'm assuming that the only thing that happened between yesterday and today is that we implemented this new policy. Right? I'm assuming that everything else about the world was exactly the same a year ago as it is exactly the same now. And as somebody who lives in the US, I can tell you a year ago is not very much like now. There are some very big differences between a year ago and now. But in general, there's lots of things that are going to happen over time. And we don't, but if we just do this, we're going to attribute anything that happens over time to the policy. Okay? So that's going to be the problem with the difference model. So that's why we're going to do difference in differences. Are you guys with me on this? You were talking, before the break, people were talking, and now people are more quiet. We learned that tomorrow you don't get a break. Okay, so this is the problem. Anything that happens between time 0 and time 1, we're going to attribute to the program. But there's lots of stuff that happens, and usually programs that we're looking at are relatively small, right? I mean, if we're looking at the U.S. between last year and this year, Trump being president is a relatively large thing, and you might think that made a big difference. But there's a lot of small things that happen as well, and we wouldn't want to attribute all of those things to just the one policy. And in particular, if I added time effects into the model, I couldn't separate the time effects from the treatment effect, right? It's perfectly collinear. The treatment effect varies perfectly over time. So what do I need for difference in differences? I need the treatment effect to no longer be perfectly collinear with time. Okay? And in particular, the simplest version of it is I'm going to have 2 groups of people. So now I'm going to have diamonds. Now I'm going to have diamonds, and I'm going to have clubs. I made these slides when I was really bored. For some reason, you're going to see the colors are going to come out. We're going to continue to have blue clubs and red diamonds. So the big thing here is that we're going to have 2 groups of people. We're going to have the diamonds, and the diamonds are going to be just like you guys were in the previous experiment. The diamonds are people that are affected by the policy. Okay? But what's also important is now you have a bunch of clubs, and the clubs are in this other classroom over there. They're kind of similar to you. They're not exactly the same as you, but they're kind of similar to you. But they're not affected by the policy change. Okay, so they don't have to be the same as you. They can be a little bit different than you. But the key thing is you were affected by both the policy change and time. These guys were only affected by time. Okay, so you can see where we're going to get the difference in differences. When I look at before and after for this group, what do I pick up? If I look at before and after for this group, I'm going to pick up the policy effect plus everything else that happened over time. Okay? If I look at this group, there's no policy effect, so all I'm going to have for this group is everything that happened over time. So this gives me policy effects from time effects. This difference gives me policy effects plus time effects. This difference gives me time effects. So the difference in difference gives me only the policy effect. Okay, so in particular, I can think about estimating. The problem with what I did with the difference model is I was picking up time effects plus the policy effect. I'm going to use this thing to estimate the time effect, and I'm going to subtract it, which is going to give me only the policy effect. Okay, so a little bit more formally, we're going to do a model in the following way. You're going to see something else Tabor specific, because I care very strongly about subscripts here. People like to have like 7 subscripts on their Y's, and it just kind of drives me crazy. There's really 3 things. So there's the group. So the groups in our example, there's this classroom and there's a classroom over there. So you're either in this classroom or that classroom. There's an individual I which picks up a person, and then there's the time effects. We're going to observe the same people over time. So I'm assuming we have panel data. So I want an IT subscript. Everything should be measurable with respect to I and T. If I know who you are, I know which group you belong to. So some people would write this as YIST. I prefer to write it as YIT, where S of I is going to say to which classroom does person I belong. Or in the notation that I have here, where I have suits, to what suit are you? Are you a heart? Are you a diamond? So we're going to allow, this is going to be the treatment effect. We're going to allow for a time effect. It looks like linear. It's not linear because T is a dummy variable. So this is a dummy variable for being in time 1. This is going to be the individual fixed effect once more. And then we're going to have the epsilon IT. SII is going to say what your suit is. Further, we're going to assume that TST takes the following form, and it's what I've said verbally. The clubs never get the treatment. Okay? For the diamonds, the treatment moves from 0 to 1. Okay, so for all of the diamonds, it's 0 in period 0, and it's 1 in period 1. T is no longer. We couldn't estimate this model before because T would have been perfectly collinear with capital T would have been perfectly collinear with small t. Crappy notation. Sorry, but. Using anything other than capital T to be a treatment is kind of dumb. Using anything other than a small t to be time is dumb, but so we get 2 t's. Anyway, these things would have been perfectly collinear before, but now because we have the clubs, they no longer are. We're going to have some group of people for which this thing does not change while this thing does. So now if we just do our difference and difference, if we do our difference and difference of this thing, we're going to end up just taking that equation before. For the diamonds, you're going to get a beta naught plus an alpha plus in period 1. For the diamonds in period 1, you get alpha and delta. You always get a beta naught, and then you're going to get their theta. In period 0, you're going to get a beta naught, no alpha, no delta, because treatment is 0 and it's period 0, but the same theta, right? It's exactly the same population. So notice that thing is going to difference. The beta naught is going to difference. So when we look at the diamonds, what we get is the alpha plus delta. So this is the treatment effect plus the time effect. For the clubs, there's no alpha, so you can get exactly the same thing, except there's only a delta here. So you get alpha plus delta minus delta is equal to alpha. Okay? And that's difference in difference. That's why difference in difference works. So what's the key assumption that gets this to work? Okay, it's pretty nice, right? I mean, notice that this thing and this thing do not need to be the same. Right? That is, the diamonds and the clubs can look different from each other. I don't need to have random assignment of diamonds and clubs. As long the fixed effects for the diamonds and the fixed effects for the clubs can be completely different. It doesn't matter. It's going to difference away. The first differencing already took care of that. Okay, so that's the main problem that I worry about, is that if I only have diamonds and clubs, that they're different kinds of people, but that's disappeared. We've gotten rid of the fact that they're different kinds of people. So that's not a problem. What's the key? I mean, it's kind of looking at this. What's the key assumption here? So what does that mean here? So you're right. That's right. But what does that mean in terms of this slide? Essentially means they have the same delta. Right, what I need is that I could write the mod, whoops, oh, shoot. For some reason this works. If I made a diamond here, diamonds are easy to draw. Clubs are like really hard to draw, and I'm very drawing challenged, so that's a club. So if I had if this is the delta for the diamonds and this is the delta for the clubs, what I need is the delta for the diamonds is the same as the delta for clubs. So what I need is the effect. The effect that the changes over time for the diamonds is exactly the same as the changes over time for the clubs, which is exactly the assumption that you're talking about. So the difference of difference is that the deltas cancel. But if the deltas for if what happens to you guys over time is totally different than what happens to that classroom over time, the way you experience time different, there's other policies that affect you that don't affect them, or just you guys are young and are going up in the world, while those guys are old and they're kind of going down in the world, then it's not going to work. Okay? So the diamonds don't have to look exactly the clubs in the sense the differences can be, the levels can be different. They can have different levels of theta, but they have to have parallel trends. That is, they have to, the changes over time for the diamonds has to be the changes over time for the clubs. Otherwise, you're going to get a bias here and this won't difference. Okay? So really the crucial assumption to get difference and difference to work is that the clubs do a very good job of picking up what this thing is. If they don't do a good job of picking up what this thing is, then this thing is not going to work. Okay? For a lot of problems that we're worried about, this is a pretty reasonable assumption. Okay? It doesn't always work. If you have if the diamonds are totally different than the clubs and they experience the world in different ways, it's generally not going to work very well. But this is an example of something that's pretty that tends to work pretty well. Okay, this is what I just said with my color. I'm good with a computer making colored stuff. I'm bad with a pen writing stuff at all, which is why I'm the guy teaching you with a pen. So this is the intuition. How do we implement this? The way that we're going to generally implement this is there's two ways to do this. If you have panel data, you can literally just stick in fixed effects for people. If you have repeated cross-section data, it's okay. If you have repeated and you can kind of see this, you can see this in this picture here. To get this identification to work, we didn't need to have exactly the same people. We need to have exactly the same population. So as long as you have a random sample of diamonds in period 1 and a random sample of diamonds in period 0, these two things are going to cancel, and the same thing for clubs. So I can do this. I can do this with repeated cross-section data. I don't have to have panel data. I have to know who a diamond or a club is. That is, for the people who would get in period 0, I have to know who the people who would be eligible for the program in period 1 are. Right? If I repeated cross-section data, I need to know something about eligibility. So that requires something. But as long as I can identify what the groups are, that is, as long as I know what your suit is, I can just stick in dummy variables for suits. I don't have to have literally fixed effects. Okay, more generally, if I'm going to implement it this way, notice I can do a whole bunch of stuff as well. I can add x's into I can estimate this as a regression model. I generally am going to stick in time dummies and group dummies. I do not need to restrict myself to binary treatments. I do not need to restrict myself to 2 different time periods. I can do much more general models. What we call difference in difference, it got the name for this simple 2x2 thing. When I refer to difference in difference, I say this is like 90% empirical work. I'm talking about a much more general specification when people run models where they include time dummies and group dummies, and then they have some treatment. And the key thing is this treatment thing only varies with the group by time level. Right? There's no variation of this within the group. So if I know your group and I know your time, I know what your treatment is, and I can estimate the effect. So this is difference in differences. This is super important, and something that it works particularly well in the U.S. because we've got 50 states. The states change their policies. The states change the policies a lot. That's a big number, and people often use that. How many provinces? I'm embarrassed. How many provinces are there in China? Yeah. So again, for China, if you're thinking about policies that change in some provinces and not in others, that this is the sort of thing that's going to work well as there. It's not quite as many, and there might be there's more heterogeneity across provinces in China than there is heterogeneity across states in the United States, I think. But still, it's something you can do there. You can do it with different countries. You can have different groups. So there's a bunch of different ways. There's a bunch of different ways to do this. So this is difference of differences. I'm going to give you an example, but any other questions about this? Okay, so the paper that I want to talk about is, if you've read Freakonomics, you've heard of this example. This was the paper that made Steve Levitt Mr. Freakonomics. So this was at the time this paper was published, it was like on the front page of the New York Times. It got all kinds of attention. And I think everybody hated it. I can talk about why everybody hated it a little bit. Essentially, what they did is the following. Well, I can motivate it with the data. So these are crime rates in the United States. So this is violent crime, property crime, or murder. They're all on the scale, so there are 100 in this period. There's a lot fewer murders than there are property crimes, but they're on the scale of 100. To get a sense of how they change. And what you see in the data is that crime rates went down a lot in the 1990s, and it's been good. So it's continued to go down, gone down since then. So what you see is this really relatively large change in crime rates that fell during the 1990s. So what Donahue and Levitt want to do is they want to understand what it was that drove this decrease in crime rates. Okay? And here's where they have a really creative solution. So in 1972, there's a Supreme Court case that talked about abortion. So prior to 1972, abortion was illegal in the vast majority of states in the United States. In 1972, this famous Roe v. Wade decision, the Supreme Court said, no, abortion is a right. Every woman who wants an abortion should have the right to have an abortion. Okay? So what Donahue and Levitt did is they want to say that Roe v. Wade was the explanation for this thing. Okay, that's kind of goofy. So why would, especially because Roe v. Wade happened back here. Okay, so why would Roe v. Wade potentially explain this? The argument is that a lot of the people, it's a little bit of a local average treatment effect, a lot of the people that were affected by the Roe v. Wade decision were relatively poor women. So a lot of the women who, a lot of rich women had access to abortion, even though it was illegal, a lot of rich women had the access and the ability to get abortions anyway. So a lot of people who were affected were like single moms, single teenage moms who didn't really necessarily have resources. So the argument here is the people that were aborted were people who would have been born to poor single moms. Those people would have grown up in a poor, those people would have grown up in a family with bad socioeconomic status, neighborhoods, and would have grown up and had relatively low socioeconomic status themselves, and would have been relatively more likely to be criminals. I said that really poorly. The argument is the people that were aborted were people that were likely to commit crimes. So the reason that the crime rate fell is that we had abortion rates where a bunch of potential criminals are now being aborted. Okay, does that make sense? Okay, you can see why the politics in the U.S., both sides hated this. So Republicans hate abortion. So this idea that there's something potentially good about abortion, they kind of hated the idea that this was good for abortion. Democrats hate it because it kind of sounds like we're getting rid of criminals. It sounds like genetic manipulation of people in order to get rid of potential criminals. So so kind of everybody hated this. But it's a potentially really potentially creative idea. And just because you hate it and don't think it's an uncomfortable thing to think about doesn't mean it's wrong. Has anybody ever watched the show Orange is the New Black? So there's a scene in Orange is the New, there's a scene in Orange is the New Black where they talk about this paper. And it's the only time that like somebody I know as an economist was referred to in a popular TV show. It's like two criminals and it's Mother's Day, and one of the moms is really depressed because she had 5 abortions, and she's all depressed. It's Mother's Day. She has little crosses laid out for all the abortions. The other woman comes and comforts her, saying, no, that's all right. I read Levitt. Your kids would have grown up to be criminals anyway, so the fact that your kids weren't born was good for the world. And somehow, this comforted her. She felt much better about it after that. Anyway. Okay, so identification here is going to come from the fact that prior to Roe v. Wade, abortion was legal in some states. Okay, it was only legalized kind of in the late 60s. So it hadn't been legal for long, but it was legal in New York, Alaska, Hawaii, Washington, and California prior to Roe v. Wade. Okay, so this is a case where you have a difference model. The New York, Alaska, Hawaii, Washington, and California, this is one of these cases where thinking about who's the treatment and who's the control is a little bit complicated because it switches who has it and who doesn't and exactly what you want to think about the treatment. But the fact is that these guys, for a while, these guys had abortions while the other ones didn't. So these guys were the early adopters. Abortion was legal before that. So if this is an important thing, what we should see is that the decrease in crime rate should happen in these 5 states prior to the other states. Okay? So if the Roe v. Wade, if the abortion is the example for the crime rate, we should first see crime rates decline in these states and then decline in the other states later. Okay? So the problem with this identification strategy is what is before and after, right? You can look right before Roe v. Wade and right after Roe v. Wade, but that doesn't work well because generally newborns are not the people that commit crimes. Usually the people that commit crimes are going to be people that are older. So what they do is they create an effective abortion rate for state J at time t by looking at whether abortion was legal and then looking at the age at which people commit crime. For example, if people only committed crime at age 17 and at age 17 only, you would look 17 years after abortion was legalized and see if you find a jump there. Okay? Because it's not only 17, it's going to be a little bit different. But this thing happens, I think 13-year-olds do not commit crimes at really high rates. 16-year-olds commit crimes at very high rates, so it spikes up pretty quickly. So they're going to use this effective abortion rate. That's going to be their treatment. They're going to have a bunch of X's they can put in the model. They're going to put in state dummies and put in time dummies, and this is an example of difference in differences. Okay, does this make sense? Okay, so what do they find? I'm going to show you what they find. This paper has been criticized for lots of reasons, one of which is being sloppy. So if you're super interested in this, you should read this paper. You should read some of the criticisms and make your own decisions. But here's an example of abortion. So 72, you see Roe v. Wade, and then abortions go up after that. One thing to recognize is important is that you're not going to get abortions immediately after Roe v. Wade because you actually have to have an abortion clinic. You need to have a place to go where you can get an abortion. So it took a while before they started to build the abortion clinic. So this thing didn't happen overnight. There was the crime rate. So here is the easiest way to see it. So what we're going to look at, so it doesn't matter which thing we look at, we'll focus on violent crimes. So we see what's happening in the 80s. In the 80s, this is prior to the kids being old enough to commit crimes or at very low levels. These things were essentially the same, and they're very similar in the years prior. So prior to this abortion kicking in, these states were looking pretty similarly. Then 1988 to 1994, this is going to be a period where the abortion rate is starting to kick in these 5 states, but not in these other states. And what you can see is that the plateau happens earlier. So essentially this big increase in crime that we see stopped in these states during this time period, but continued to rise during this time period. And then if you look at the final time period, it was decreasing much faster in this time period than it was in this time period. Okay, so if you do your difference in differences, this is a difference. This is a difference for one group. This is a difference in the other. This is the difference of difference. Okay, so you can see that it looks like there was a much bigger decrease in crime in the states that implemented abortion changes earlier, that legalized abortion earlier, than there was in the states that did it later. And it doesn't matter which outcome you look at, you're going to see similar things. So that's the difference version. Here is the regression version of it, and you can see that they find relatively large effects of abortion on crime. Questions? Okay. How much time do we have? We only have 25 minutes? Shoot. Okay. Last design-based thing that I want to talk about is regression discontinuity. So this is an old idea. So you can find the ideas of regression discontinuity. There's this Cook and Campbell talk about it. It goes back before that. So the idea is relatively old. In economics, it's really taken off recently. So this is, in the last 10 years, regression discontinuity has become the hottest thing and one of people's favorite ways to estimate models. So what it's going to take advantage for is, for a lot of policies, the way the treatments work is that they're going to have some cutoff. So there's going to be some cutoff that says if your income is below this level, you don't have to pay any tax, but if your income is above this level, you suddenly have to pay the tax. So a lot of policies are work this way. So as this is one of these things where it's lucky, as economists, we're lucky that economists aren't in charge. Because if economists were in charge, we wouldn't have rules like this. Things would be nice and smooth. But because economists aren't in charge, we get a nice identification thing because there's lots of different policies that are going to work something like this. So often tests, there's a passing grade. So if your grade is above some number, if your grade is above some number, you get into college. If your test grade is below some number, you don't go into college. And some of you are familiar with this, I think. Whether you're eligible for a program or not, you'll have income cutoff. So if your income is above this number, you're not eligible. If your income below is, you're eligible. Whether you win an election or not, 50.00.1% of the vote, you win. 49.999, you don't win. Which school district you reside in. In the US, it's changed actually. But in the US, it tended to be, we would divide school districts. So if I was in this side of the street, I go to that school. And if I'm on that side of the street, I go to that school. Punishment strategy. So there's punishments that say if you're carrying, I don't even know the right numbers, 1.5 grams of cocaine, it's a felony. If it's 1.4999, it's a misdemeanor. Birthday for entering kindergarten, so whether you start school often depends on exactly what day you were born. So there's lots of examples of things that a very small change can lead, a very small change in the X variable can lead to a very large change in the treatment. So to think about identification, it's pretty easy to think about. So here's our model. We're going to be in the constant treatment effects world. Yi is me beta naught plus alpha t plus epsilon. So let's not worry about other x's for now, though we can if we want. All we're going to need is one assumption. The only assumption that we're going to need is that the expected value of epsilon conditional on x is going to be smooth. Okay? And it's be differential. It's going to be actually continuous. It doesn't even have to be differentiable. As long as this thing is smooth, you're going to get consistent estimates of the model. So to see how this works, remember that when x is below x star, you don't get the treatment. When x is above x star, you do get the treatment. So let me think about the expected value of y conditional on x. And I'm going to take that limit from below, and then I'm also going to take that limit from above. Okay, what do I get? I'm going to get, when I take it from below, t is always equal to 0 because x is always below x star, so I never get alpha. Then I can get beta naught plus this thing. Well, this thing is going to converge to that object there. Okay? When I take it from above, x is always bigger than x star, I'm going to get alpha. I get this object here, that's going to converge to that. Well, notice that beta naught is the same. Those two objects are the same. So the difference in these two things is going to give me consistent estimates. So what am I doing? I want to look at people just to the right of the cutoff and just to the left of the cutoff. And that's going to give me a consistent estimate of the effect. So that's a regression discontinuity. OK? Makes sense? These are really nice when you can find them. That's what's called a sharp regression discontinuity. So it's a sharp regression discontinuity in the sense that if x is bigger than x star, I've assumed that ti is always equal to 1. If x is less than x star, I've assumed that ti is equal to 0. It rarely works that way. So typically, there's some rule, and the rule says, you know, if you were caught speeding above 70 miles an hour, you get a $30 fine, and 69, you get a $20 fine. But the people that got the $30 fine sometimes sweet-talk the police officer into giving them the $20 fine, so on and so forth. So usually you can sweet-talk your way out of this exact thing, but not everybody does that. Okay? So as long as there's some people that are affected, it'll still work. That is, as long as the probability of getting the treatment when you're just below the line is strictly smaller than the probability of getting the treatment where you're just above the line. It's still going to work. It's just you're going to take a ratio rather than just look at the numerator, which is what we were doing before. This should look somewhat like IV, and in fact, it's exactly. This is essentially the first stage in IV, and this is the reduced form. In IV, and we're just essentially estimating the Wald estimator. Okay? And T can be continuous. It doesn't need to be binary. You control for other models. It's relatively straightforward. So this is regression discontinuity. That's the idea of it. How do you do it in practice? There's really, I said I wouldn't talk about practice. There are really two different ways to do it. One way to do it is, I'm going to show you the same picture and show you two ways to do it. What we want to look at just to the right of the line and just to the left of the line. So what we do is we find the line. The line's going to be there. And then we're going to look to the people just to the right. And we're going to look at the people just to the left. We're going to take the sample mean of the people just to the right. We're going to take the sample mean of the people just to the left, take the difference between those two things, and that's going to give us a consistent estimator. We need the distance here is going to shrink. So we're going to do something like a kernel estimator. It turns out that it's better if you do something like local linear regression than a simple kernel estimator, but that's essentially the idea. So that's idea number one to implement it. When people think about regression discontinuity, this is what they have in mind. But there's another way to implement it, which in some ways is more straightforward and is just as legitimate a way of implementing IV. So to see the second approach, just let me define g of x to be the expected value of x conditional on x. Okay, we know g of x is smooth. So this is something that I know about g of x. And then just think about the expected value of y conditional on x. The expected value of y conditional on x is beta. We're in the sharp case. It's beta plus this object here, right? Alpha. I know that t takes on this object, so I know this thing, and then I have this nice smooth function. So another way that I can think about implementing this is just running a regression of y onto a nice smooth function of x and a dummy variable for whether x is bigger than x star. So what does that look like in the picture? Essentially what you're doing in the picture is you're estimating this line here, right? This nice smooth curve. So what we'll typically do is we'll put in something like a polynomial here, a dummy variable for being bigger than x star, and we can estimate the model just by looking at the coefficient on this dummy variable. It's actually really, really easy to do this IV. You use the dummy variable for whether you're above or below x star as an instrument for the treatment itself. So you can just implement this thing by IV. Notice when you do this, you're using all of the data. You're not only using the observations that are really close. This thing is just as legitimate and just as non-parametric. It's when you're doing it the kernel way, you're promising to shrink the kernel as your sample size gets large. When you're doing it this way, you're going to have your g of x is going to be some polynomial. You're promising to add terms to your polynomial as your sample size gets large. So both of them are legitimate ways to estimate this. In practice, people do it both ways. Okay, so that's RD. Questions about RD? Another super famous, okay. I have a problem slide first. Problems. So there's three potential problems with RD that might arise. The one is kind of obvious, is that this is really data hungry, right? You want to have a lot of observations. I mean, going back to this picture, you want to have a lot of observations that are really close to this line. And if this thing is not, I mean, if this red line and this green line, if they weren't very smooth, right, then you need lots and lots of data. So sometimes we just don't have that much data. So sometimes, in principle, it's a perfectly good identification strategy. Asymptotically, it's going to work fine. But as a practical matter, our bandwidth, the set of observations that we're using to approximate this thing, is so large that it's not really regression discontinuity. Okay, so I don't necessarily believe it. That's problem number one. The second problem is sometimes it happens, sometimes it doesn't. Sometimes there's other things that happen at exactly the same time. So for example, the Pell Grant in the US is something that's given to poor people. Whether you're eligible for Pell Grant depends on whether your income is below or above the poverty line. Okay, so the cutoff is the poverty line, but there's lots of other policies that depend on whether your income is just below or above the poverty line. So you're not just only picking up this policy, you might be picking up other things. Another example, and I had a student who looked at this in Korea. He was looking at kindergarten start age. So the age at which you start kindergarten depends on whether you're born right after midnight or right before midnight on January 1st. So what year you're born depends when you start kindergarten. But in Korea, I guess your age depends on the year in which you're born. So not only does changing the year in which you're born changes your age and the way that you're treated in Korea. So that's another example. There's other stuff happening at the same time. The biggest threat is manipulation of the running variable. So if I know that I get the policy if my income is above $10,000 and I don't if it's below, I might work a little bit more to get my income a little bit higher. Okay, so if I know what the policy is, if I can manipulate the running variable, I might want to change things. So an example, suppose that carrying 1 pound of drugs was a felony, but less than 1 was a misdemeanor. I would be a moron to be carrying 1.001 pounds of drugs, right? So anybody who knew what this rule was and anybody that knew how to count things is going to make sure that they're carrying below. Either they're going to carry 10 pounds where they're not even close, but if they're a little bit above, they're going to carry a little bit less just because if they're caught, they'll be less vulnerable. They won't get charged for the crime. So the only people that are going to be carrying 1.01 pounds of drugs are going to be kind of stupid criminals. Okay? So then your regression discontinuities are going to work because you're comparing stupid criminals, who are the people that are above, to the people that are below, which include both stupid criminals and smart criminals. Okay? So if you can manipulate, another example, if I say that I have an exam, that if I have a paper and I tell you that my paper is due at exactly 5 o'clock on Thursday afternoon, interesting time. If I tell you that it's exactly 5 o'clock on Thursday afternoon, at 4:59 there's going to be a lot of papers that I haven't gotten yet. At 5:01 there's going to be almost no papers that are turned in late. So people manipulate things. It turns out David Lee has a paper that basically shows in order for this to be a problem, you need to be manipulated exactly. Okay, you need to be able to precisely manipulate the running variable. So it's not that if a lot of the cases we're worried about, you have some control over the running variable, but you don't have exact control over the running variable. So if you have some control over the running variable, but not exact control, you're still fine. You're still going to get consistent estimates. Okay, so let me give you an empirical example real quick, and then we'll cover structural estimation in 5 minutes. Angris has made a career of coming up with really creative papers, and he has a lot of them, and this was one of these. This is a paper with Victor Levy. So the Talmud is like the Bible for, I don't know how to say this without the right. I don't want to sound like I'm saying it the wrong way. It's like the Bible for Jewish people, which seems like an insensitive way to say it, but I'm trying to think of a better way to say it, and I can't. So they interpret. So Maimonides was a 12th century rabbinic scholar. So he was a Jewish scholar, and he interpreted the Talmud in the following way: is saying that 25 children may be put in charge of one teacher. If the number in the class exceeds 25 but is not more than 40, he should have an assistant to help with instruction. If there are more than 40, 2 teachers must be appointed. Okay, so what's he saying? He's saying if you have 41 students in a class, you have 2 teachers. But if you have 39 students in a class, 1 teacher is enough. Okay? This sounds like a regression discontinuity. And Angris and Levy were smart enough to figure out that, yes, this is a regression discontinuity, and they can use it as regression discontinuity. For example, if you have 80 kids in a grade, you can have 2 classes with 40 each. But if you have 81 kids in a grade, then you have to have 3 classes that have 27 kids in each of the class. So you get this regression discontinuity. So whether I belong in a class with 81 kids or 80 kids is going to affect the size of my classroom. So they're going to use this regression discontinuity to measure the effect of class size on outcomes of kids. The way they write the rule. We don't have much time, so I can go. This is the mathematical expression for Maimonides' rule. So if you figure it out, it's going to. If you stick in the number 80, you're going to get 40, and if you stick in the number 81, you're going to get 27. So that's how that thing works. They're going to implement this in both ways. I basically already said that. Here is Maimonides' rule versus the actual class size in Israel. So it's a Jewish rule. So where they're going to follow this most closely is going to be in Israel. So what you see in this jagged thing is the actual class size you see in the data. What the dashed line is Maimonides' rule. So it's graphing the F thing. So what you should see is that you can probably figure it out. So this is 40 and this is 80 and this is 120. So these are these places where you see big drops in class size, and you can see that you see big drops in class size right around these cutoffs. So the higher, it's harder to see it at the larger classes. So this is for 5th grade. Here's the same thing for 4th grade. So it works pretty well. Here's a graph. It looks much nicer than it actually is because the way they divided the data. But what you should see is these things should be mirror images of each other. So at the point in which the predicted class size drops a lot, you should see test scores go up a lot. Okay? And it's almost amazing. Right at this point, you see things go up. It's a little bit of an optical illusion because he's only showing things in like every 5-year bins. So these are piecewise linear. So the point where this switch has to be the point where that switches. However, the fact that goes down doesn't mean that has to go up. But you see that it works really well. When this thing is going up, that thing's going down. When that thing's going down, that thing is going up. So this suggests that class size bigger classes is a bad thing. Smaller classes leads to higher test scores, which is what we would expect. It's hard to show in data. If you just look in the data, you don't see very much. This is the same thing for 4th grade. Here are the regression results. And he does it they do it a bunch of different ways, but you consistently find. So here they use the full sample with a nice smooth function. Their nice smooth function is the quadratic. So it's enrollment and enrollment squared. Okay, though you see that. You can look at the discontinuity sample where you're looking at classes within 15 to 25. You see the effects there. This is for reading, and you see I think even you see larger effects for reading than you do for math, but you see negative effects for math as well. That is, bigger class size leads to lower tests, which is what you'd expect. So this is a classic paper on regression discontinuity. So questions about that? Okay. Yeah, so structural estimation in 5 minutes. Which is fine because I'm not going to say that much about it. What we focused on so far is the evaluation problem. So everything we focused on so far is we want to look at the effects of a policy that already exists. That is, some of the people get the treatment, some of the people don't get the treatment, and we're trying to estimate, we're trying to evaluate. So given that we've seen this policy, how effective was the policy? Now we have the selection problem. That doesn't mean it's an easy problem. We have the selection problem, so we've had to deal with that, but that's the only problem that we've been dealing with. The other problem that we want to think about now is estimating the effect of a policy that doesn't yet exist. Okay, we have some other policy that we're thinking about implementing, or we want to figure out some optimal policy, but we've never seen that optimal policy, so we don't know what it is. So what we want to do is we want to try to figure out what that is. Often that's what we care about in economics, right? Often what we try to do as policymakers is evaluate policies that have not yet been implemented and want to try to see what would happen. Okay? And this is I'm almost going to define structural estimation to be this. That is, in order to be able to estimate the effect of a policy that's never been implemented, you need enough structure on the problem to be able to solve for what that policy looks like. I think I'm going to skip this. That stuff's kind of fun, but let me just finish. Actually, I might even finish early now that I just skipped all that. Let me just write it the following way. Let's get back to our initial notation. So we have our data generating function. So this is how the world works, right? So we generate x, we generate u. I'm going to change things a little bit now. There's a zero subscript on epsilon because this is what happens when the world is generated by the current policy generating policy. This is what happens when the data is generated by the way that the data is currently generated by. Now what we want to think about is we want to think about a new policy, something that's never been implemented before, and we want to estimate the effect of that. Now we're going to have a new data generating process. The data generating process under policy pi is going to look like this. Okay? Essentially what we need for identification, if we want to identify the effect of the policy, essentially what we need is that these things are all known up to theta. Okay? Specifically, suppose that I want to identify some counterfactual that looks like this. Often counterfactuals that I might want to identify are the difference in earnings that I would get under the policy counterfactual I'm thinking about minus the status quo. So this is what happens if I change the policy. This is what happens if I leave these the same. So this looks like a treatment effect, very much the same kind of treatment effects we've looked at before. The difference is we don't have any data on this at all. Right? We have to use our model to simulate what this looks at. There's nobody in the data. There's no data that's ever been generated under this policy because this policy has never existed before. And you can see that this thing is a function of y pi. So this is the model under the new policy regime, the distribution of u under the new policy regime, the distribution of h under the new policy regime, and then this is what happens in the current data. That's one version of something we might do. We might have something ambitious, more ambitious. Maybe we want to look at not income, but something like utility, right? And then we need something that's not even directly data, but our model, we need the model itself to tell us what the utility function would be. Okay? So in practice, what do I need to identify this? Essentially, what I need for identification of a policy that's never been implemented is two main assumptions. The first assumption is that h pi, f pi, and y pi are known up to theta. So theta was my data generating process before, the parameter indicating the data generating process before. This is essentially what I'm going to mean in this set of lecture notes, or today, this is what I'm going to mean by structure. I have enough structure that I can say that if I know the current model, given that I know the current model, I can say what would happen if I change the policy. So I need enough structure on the model so that this thing, and this thing are known up to theta. Okay, does that make sense? So think about a parametric version of the model. So what I'm telling you is if I knew the parameters of the model of the current data generating process, I could simulate what would happen under the policy regime. That's what I mean by structure. So I need enough structure so that's true. That's the first thing that I need. The second thing that I need is I need theta to be identified. So I need to identify the data generating process in the current world, and it's the same theta. Right, the theta that we use to generate the data today is the same theta that would be used to generate the data in the policy regime. That's another definition of structure in the sense that we say the theta itself is policy invariant. Changing the policy doesn't fundamentally change the data generating process. So we need to identify the data generating process and that they're exactly the same. Typically, when we do structural estimation, we do it differently than we've been doing it before. So far, what we've been doing is we've been thinking about estimating treatment effects, right? We haven't been trying to estimate the model. We've been estimating the features of the model. Okay? This thing, again, we're not interested in the model itself. We're really interested in this feature of the model, this policy, the effect of the policy that's never been enacted. Typically, we can't identify that without identifying the full model. So typically, not always, but 99% of the time, when we're doing structural estimation, we identify the full model, the full theta, and then we use that model to simulate the policy. I have one last slide. How do we do that? Basically, there's two ways to do it. One is maximum likelihood, is one way of doing it. Another is simulated method of moments, GMM, indirect inference, something like that, which involves simulating the model. Both of those, you need to fully specify the model in order to implement those. So I'm done just on time. I skipped a couple slides. And Chao will finish this off. Chao is going to, I think, will pick up perfectly from this tomorrow and think about how you actually estimate a structural model.